Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring the intriguing and perhaps unsettling concept of the Boltzmann brain. Why your existence might be a random hallucination. Before we gently immerse ourselves in these profound considerations, I would like to know where you are at this moment. Perhaps you are listening while watching the gentle patter of rain against your window, or nestled comfortably in a reading nook, surrounded by the quiet company of books. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The journey into the profound nature of light begins with a number, a constant value that permeates the very fabric of our universe. This universal speed limit, approximately 299,792,458 meters per second in a vacuum, is not merely a fast speed. It is an absolute. It is a boundary that nothing in our cosmos possessing mass can ever reach or exceed. This isn't an arbitrary rule, but a deeply embedded property of space-time itself, a consequence of the intricate dance between energy, mass, and motion. To truly appreciate why this limit exists, we must delve into the insights gifted to us by Albert Einstein, particularly his theory of special relativity. Before Einstein, the ideas of space and time were largely considered separate and absolute, a universal stage upon which all events unfolded. But he revealed a more fluid, interconnected reality, where space and time are inextricably woven into a single fabric called space-time. And within this fabric, the speed of light, often denoted as c, holds a unique and unwavering position. Consider an object with mass, perhaps a spaceship, accelerating through the void. As it gathers speed, something remarkable begins to occur, something counterintuitive to our everyday experiences. Its mass starts to increase. This isn't a mere addition of material, but an intrinsic change in its inertial mass, its resistance to further acceleration. The faster an object moves, the more massive it becomes. This phenomenon is a direct consequence of the famous equation E=mc2, which eloquently demonstrates the equivalence of mass and energy. As an object accelerates, the energy imparted to it converts into an increase in its mass. Now, imagine our hypothetical spaceship approaching the speed of light. As it draws closer and closer to this cosmic barrier, its mass would grow exponentially. To reach the speed of light itself, the mass of the spaceship would become infinite. And to move an object with infinite mass would, in turn, require an infinite amount of energy. In a universe where resources are finite, even in principle, an infinite amount of energy is simply unobtainable. This elegant yet unyielding mathematical truth is why objects with mass are forever bound to speeds less than that of light. Light itself, composed of photons, has no rest mass, allowing it to travel at this ultimate velocity. It is not accelerating to the speed of light. It is born at it, and it ceases to exist when it is absorbed. This limit also profoundly influences our perception of time and space, revealing that they are not fixed, but relative. If you were aboard that accelerating spaceship approaching light speed, you would experience time passing differently than someone observing you from a stationary point on Earth. For you, inside the vessel, everything would feel normal. Your heart would beat at its usual rhythm. Your thoughts would flow at their accustomed pace. But to the observer on Earth, your clock would appear to tick more slowly. Your movements would seem sluggish, your very existence stretched in time. This is known as time dilation, a fundamental aspect of relativity, where time literally slows down for objects in motion relative to an observer. The closer you get to the speed of light, the more pronounced this effect becomes. Similarly, space itself would seem to compress. The length of your spaceship, as perceived by the stationary observer, would appear to shrink in the direction of its motion. This is length contraction. A journey that might seem incredibly long from an external perspective could appear shorter to someone traveling at relativistic speeds, as the very distances between celestial bodies would contract. Yet, for the traveler, the dimensions of their own vessel would remain unchanged. This suggests that our experience of space and time is intrinsically linked to our motion, painting a picture of a universe far more dynamic and interwoven than our classical intuitions suggest. The constancy of the speed of light also plays a crucial role in preserving causality, the fundamental principle that cause must precede effect. If it were possible to travel faster than light, one could, in theory, send information or even oneself back in time, creating paradoxes that would unravel the logical structure of our universe. Imagine receiving a message from your future self, warning you not to take a particular action, and then following that advice, thus preventing the very event that prompted the warning. Such scenarios violate causality, and the speed of light limit acts as a cosmic guardian, ensuring that the flow of cause and effect remains consistent and orderly throughout space-time. It ensures that the sequence of events, the very narrative of existence, unfolds in a coherent and predictable manner, preventing a chaotic tangle of possibilities. So, when we contemplate the speed of light, we are not merely considering a numerical value, but a profound statement about the nature of reality itself. It is a constant that defines the very architecture of space-time, dictating how mass and energy behave, how time flows, and how distances are perceived. It is a gentle reminder that our universe operates under elegant, unyielding principles, where movement is not just about changing position, but about interacting with the deep structure of the cosmos. As we drift towards sleep, let us carry this thought, that the speed of light, while an insurmountable barrier for physical travel, is also a window into the universe's most fundamental truths. A quiet hum in the background of existence, ensuring that everything remains beautifully, profoundly in its place. The preservation of causality, a silent guardian of our universe's logical flow, gently guides our thoughts toward the practical dimensions of this cosmic speed limit. For us, as beings rooted in space and time, the speed of light presents a profound challenge to our aspirations of traversing the vast interstellar ocean. Consider the nearest star system to our own, Alpha Centauri, residing at a distance of approximately 4.37 light-years. This means that even if we could develop a spacecraft capable of traveling at nearly the speed of light, a one-way journey would still take over 4 years from the perspective of an observer on Earth. For the intrepid traveler aboard such a vessel, however, the experience would be different, a testament to the marvel of time dilation. As discussed, time would slow down for them. A journey to Alpha Centauri might feel like only a few months, or even weeks, depending on how close to the speed of light they could truly approach. Yet, upon their return to Earth, if such a return were even possible, they would find that many decades, perhaps even centuries, had passed for their loved ones and for humanity. This is the essence of the famous twin paradox, not a paradox in the sense of a logical contradiction, but a deep truth about the relativity of time. It illustrates that travel to distant stars, while physically conceivable in terms of the traveler's subjective experience, becomes a journey through time as much as through space for those left behind. It transforms interstellar voyaging into a one-way passage for the individual, a profound commitment to a future utterly disconnected from their point of origin. This cosmic constraint subtly reminds us of the precious singular nature of our own temporal thread within the grand tapestry of existence. This interplay of space and time is beautifully encapsulated by the concept of the light cone. Imagine a three-dimensional graph where 2 axes represent space and the third represents time. From any given event, light expands outward in all directions, forming a cone. Everything within your past light cone represents all the events in space-time that could have causally influenced you, as light or information from them has had time to reach you. Conversely, everything within your future light cone represents all the events you can possibly influence. Nothing outside your light cone, neither in the past nor the future, can affect you or be affected by you. The edges of this cone are defined by the path of light itself, the fastest possible connection across the cosmos. It's a serene, geometric representation of our causal universe, showing us that while the universe is vast, our immediate causal reach is intimately bound by the speed of light. It defines our sphere of influence and experience, a gentle reminder of our place within the universal flow. Perhaps the most astonishing implication of the speed of light is its effect on light itself. For a photon, a particle of light, time does not flow, and distance does not exist. From the moment a photon is emitted, say, from the surface of a distant star, to the moment it is absorbed by your eye, it experiences zero time. Its journey across billions of light years is, from its own perspective, instantaneous. It is born and absorbed in the same singular moment. This is not a metaphor, it is a direct consequence of the laws of special relativity. If an object were to reach the speed of light, its proper time, the time measured by a clock moving with it, would halt. Its length in the direction of motion would contract to zero. This profound insight means that photons are, in a sense, outside of our familiar space-time. They are pure carriers of information and energy, traversing the cosmos without experiencing the very dimensions they help define for us. They are timeless messengers, connecting the most distant reaches of the universe in a way we can only conceptually grasp. This absolute speed limit also has far-reaching implications for communication across the cosmos. Any message, whether a radio signal, a laser pulse, or even a thought experiment, can travel no faster than light. If we were to send a greeting to a potential civilization on a planet orbiting Alpha Centauri, our message would take over 4 years to arrive. And if they were to respond immediately, their reply would take another 4 years to reach us. A simple hello and how are you would span nearly a decade. This inherent delay shapes our understanding of potential interstellar communication, emphasizing the profound silence and isolation that distance imposes. It fosters a contemplative patience, a deep appreciation for the vastness that separates potential minds across the cosmic ocean. Modern scientific endeavors, such as the search for extraterrestrial intelligence, are deeply informed by this constraint, reminding us that any dialogue with a distant intelligence would be a conversation stretched across immense spans of time. It is also vital to remember the universality of this constant. The speed of light in a vacuum is invariant. It is measured to be the same by all inertial observers, regardless of their relative motion or the motion of the light source. This was a revolutionary concept introduced by Einstein, departing from classical physics where speeds are additive. Whether you are standing still, moving towards a light source, or moving away from it, you will always measure the speed of light to be precisely. This unwavering constancy is not merely a peculiar fact, it is a fundamental pillar of our physical reality, an anchor in the ever-shifting sea of relative motion. It ensures a consistent framework for all physical laws, making it truly a universal constant, a steady pulse at the heart of the cosmos. As we reflect on these concepts, we find that the speed of light is far more than just a velocity. It is a defining characteristic of our universe, a constant that weaves together space, time, mass, and energy into a coherent, interconnected whole. It sets the rhythm of cosmic interactions, shapes the possibilities of travel and communication, and fundamentally dictates what we can observe and what can observe us. It is a quiet, elegant boundary that, rather than limiting our wonder, deepens our understanding of the delicate balance and intricate laws that govern our existence. And so, as these thoughts settle, we may find a tranquil reassurance in the universe's steadfast principles, knowing that even in the boundless expanse, there are fundamental rules that hold true, providing a stable backdrop for our brief, conscious flicker within its grandeur. The unwavering nature of the speed of light, as a cosmic constant, might lead one to ponder if there are any subtle exceptions or ingenious pathways that could, in essence, circumvent this fundamental barrier. While direct travel at or beyond the speed of light for objects with mass remains impossible, theoretical physics offers us glimpses into fascinating, albeit highly speculative, methods of traversing vast cosmic distances without violating Einstein's principles locally. These concepts are not about breaking the speed limit, but rather bending the very road itself. One such captivating idea is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in the year 1994. This concept, rooted firmly in the equations of general relativity, does not suggest that a spacecraft would move faster than light through space. Instead, it posits a way to manipulate space-time itself. Imagine a bubble of space-time, a localized distortion that would contract space in front of the vessel and expand space behind it. Within this warp bubble, the spacecraft itself would remain stationary relative to its immediate surroundings, moving at ordinary sublight speeds. However, the bubble, carrying the ship within it, could effectively traverse vast distances at speeds that appear superluminal to an outside observer. It's akin to standing on a moving walkway. You are walking at a normal pace, but the walkway itself is carrying you much faster. This theoretical elegance avoids the problem of infinite mass and energy because the ship itself isn't accelerating through space to light speed. Yet the energy requirements for such a feat are truly astronomical, far beyond our current technological capabilities, often requiring quantities of exotic matter with negative energy density. It remains a beautiful, tranquil thought experiment, a testament to the flexibility of space-time, but one confined to the realm of deep theoretical exploration. For now. Another captivating idea that frequently surfaces in discussions of cosmic travel is the concept of wormholes. These are not methods of exceeding the speed of light, but rather hypothetical shortcuts through the fabric of space-time, connecting two distant points instantaneously, or nearly so. Imagine folding a piece of paper and piercing it with a pencil. The pencil creates a direct path between 2 points that were far apart on the two-dimensional surface. In a similar vein, a wormhole would be a tunnel through the higher dimensions of space-time, linking two disparate regions of our three-dimensional universe. Traveling through a wormhole would not mean moving faster than light, but simply traversing a much shorter path. The journey within the wormhole itself would still be at sublight speeds, yet the overall effect would be a near instantaneous leap across light years. The existence of wormholes, however, remains purely theoretical. If they do exist, their stability would likely require the presence of exotic matter with negative energy, similar to warp drives, to prevent them from collapsing the moment something attempts to pass through. They are ethereal bridges in the cosmic imagination, offering a serene, almost dreamlike passage across the universe, yet their construction and stability present immense, currently insurmountable challenges. Then there is the intriguing phenomenon of quantum entanglement, which often leads to misconceptions regarding faster-than-light communication. When two particles become entangled, they become intrinsically linked, sharing a common fate regardless of the distance separating them. If you measure a property of one entangled particle, such as its spin, the corresponding property of the other particle is instantaneously determined, even if they are light years apart. This seems to suggest information transfer at superluminal speeds. However, a crucial point here is that no information, in a meaningful, controllable sense, can be transmitted faster than light, using entanglement. While the states are correlated instantaneously, there is no way for one observer to manipulate their entangled particle to send a specific message to another observer faster than light. You cannot choose the outcome of your measurement to encode a message. The outcomes are inherently random, only becoming known upon measurement, thus preserving the universal speed limit for communication. Entanglement, therefore, is not a loophole for superluminal messaging, but rather a profound illustration of the non-local nature of quantum reality, a silent, interconnected dance of particles across the cosmos that quietly respects the rules of causality. Beyond these theoretical constructs, our observations of the universe itself present phenomena that, at first glance, might seem to defy the speed of light. Consider the expansion of the universe. Distant galaxies are observed to be receding from us and from each other at speeds that appear to exceed the speed of light. However, this is not a violation of Einstein's principles. These galaxies are not moving through space at superluminal velocities. Rather, the space between them is expanding, carrying them apart. Imagine dots on the surface of an inflating balloon. The dots themselves are stationary on the surface, but the distance between them increases as the balloon expands. Similarly, the fabric of space-time itself is stretching, causing galaxies to drift further apart. This cosmic expansion, driven by dark energy, is a large-scale phenomenon that does not imply objects are breaking the local speed limit. It simply means that the vastness of the universe is growing, defining a cosmic horizon beyond which light from certain regions will never reach us, regardless of how long we wait. This grand, gentle stretching of the cosmos is a reminder of the dynamic, evolving nature of our universe, a silent, ceaseless unfolding that shapes our observable reality. Finally, to deeply understand why mass prevents something from reaching the speed of light, we can touch upon the role of the Higgs field. This pervasive quantum field, theoretically predicted by Peter Higgs and others, gives fundamental particles their mass. Particles interact with the Higgs field, and this interaction imparts inertia or mass to them. The stronger the interaction, the more massive the particle. Photons, the particles of light, do not interact with the Higgs field and thus remain massless. This is precisely why they can travel at the speed of light. Any particle that interacts with the Higgs field, acquiring even a minuscule amount of mass, becomes inherently bound by the speed limit, needing infinite energy to reach c. The Higgs field, therefore, is the subtle, invisible hand that explains a fundamental part of the universe's speed constraint, a deep, quiet mechanism underlying the very nature of existence. It is a profound, elegant explanation for why some things are destined to travel at light speed and why others are forever held just below that ultimate velocity, each playing their role in the cosmic ballet. These concepts, from the bending of space-time to the whispers of quantum correlation and the deep origins of mass, illustrate that the speed of light is not merely a number, but a profoundly integrated element of the universe's architecture. It shapes the very possibilities of reality, gently guiding the flow of events and the nature of all interactions. It is a constant that, even when approached through the lens of theoretical circumvention, only further reinforces its fundamental role, creating a harmonious and logically coherent cosmos in which we, as conscious observers, quietly exist. The profound implications of light's ultimate speed extend far beyond the mechanics of individual particles or hypothetical spacecraft. They fundamentally define our very perception of the universe. This cosmic speed limit, you see, is not just about how fast things can travel, but about how much of reality we can ever hope to observe. Because light, even at its astonishing speed, takes time to traverse the immense distances of space. Every photon that reaches our eyes from a distant star or galaxy carries with it a story of the past. When you gaze up at the night sky, you're essentially looking into a cosmic archive, witnessing events that unfolded millions, even billions, of years ago. The light from the Andromeda Galaxy, our nearest large galactic neighbor, takes approximately 2.5 million years to reach us. What we see tonight is not Andromeda as it is now, but as it was 2.5 million years ago, a snapshot from a distant epoch. This temporal delay means that there's a limit to how far back in time we can see, defining what we call the observable universe. Beyond a certain boundary, roughly 46.5 billion light-years in radius, light simply hasn't had enough time since the Big Bang to reach us. It's a vast horizon of unseen history, a quiet reminder that the universe extends far beyond our current observational reach, unfolding its grand narrative in a silent, patient manner. This concept truly brings home the idea that our personal now is a local phenomenon. There is no universal present moment shared across the entire cosmos. Imagine two distant observers, each looking at the same celestial event. Because of the vast distances and the finite speed of light, they will witness that event at different points in their own local timelines. What is past for one might still be the future for another, depending on their relative positions and motions. This isn't a trick of perception, but a fundamental truth of space-time, a beautiful, intricate dance of relative realities. It invites a contemplative quietude, a recognition that our own existence is a unique thread in a tapestry of countless unfolding moments, each observer experiencing their own sliver of cosmic time. And when we consider this, the enormity of what we can see, the ancient light that has traveled so far to reach us, becomes even more precious, a testament to the universe's enduring story. Now, while we speak of the speed of light in a vacuum as an absolute constant, it is important to clarify that light can and does travel slower when passing through a medium, such as water, glass, or even Earth's atmosphere. This apparent slowing down, however, is not a violation of the universal speed limit of c. The speed of light in a vacuum remains constant. What happens when light enters a medium is that its photons are constantly absorbed and re-emitted by the electrons in the atoms of that material. Each individual photon still travels at c between these interactions, but the cumulative effect of these delays, these tiny moments of absorption and re-emission, causes the overall or effective speed of the light wave to decrease. It's like a runner on a crowded street. They might sprint at their top speed between obstacles, but the constant stopping and starting to navigate the crowd makes their average speed much lower. This gentle interaction between light and matter is what gives rise to phenomena like refraction, where light bends as it passes from one medium to another, creating the shimmering effects we see through water or the sparkle of a prism. It is a nuanced dance, a quiet interplay that enriches our visual world without ever compromising the fundamental, unyielding speed of light in the emptiness of space. This distinction leads us to another fascinating, almost poetic phenomenon: Cherenkov radiation. This occurs when a charged particle, such as an electron, travels through a transparent medium like water at a speed greater than the speed of light in that particular medium. It's not faster than c, the universal speed limit in a vacuum, but faster than light's effective speed in that specific material. When this happens, the particle creates a kind of light boom, analogous to a sonic boom produced by an aircraft, breaking the sound barrier. The radiation emitted is often a beautiful ethereal blue glow, visible around nuclear reactors or in special scientific experiments. It's a serene, silent cascade of light, a gentle whisper of energy released when a particle briefly outpaces the local speed of photons. This phenomenon beautifully reinforces the absolute nature of c in the vacuum, while also illustrating the rich and varied ways light interacts with the world around us. A subtle reminder that even within strict physical laws, there are moments of unexpected beauty and subtle defiance. The very structure of space-time is also intrinsically tied to the speed of light through the concept of the space-time interval. While observers in different frames of reference will measure different distances and different durations of time between two events, a remarkable truth emerges. The space-time interval itself remains invariant. This interval, a combination of space and time measurements, is an absolute quantity, agreed upon by all observers. It's like the diagonal distance across a room. Even if two people measure the length and width differently due to their perspective, the overall diagonal distance remains the same. The speed of light acts as the conversion factor between units of space and units of time in this four-dimensional geometry. It's the intrinsic constant that links all measurements in space-time, providing a fundamental bedrock of reality that transcends individual perceptions. This deep mathematical elegance underpins our universe, offering a sense of profound order and consistency. a quiet reassurance that beneath the apparent relativity of our experiences, there lies an unwavering, interconnected truth. In essence, barrier, but a foundational principle that sculpts the very universe we inhabit. It dictates the rhythm of cosmic communication, shapes the horizons of our knowledge, and underpins the intricate relationships between mass, energy, space, and time. It is a constant that, in its quiet omnipresence, ensures the coherence and logical unfolding of all cosmic events. As we contemplate this ultimate speed, we might find a deep sense of calm, understanding that the universe in its vastness and complexity operates with an elegant simplicity, a set of unyielding rules that allow for the beautiful, intricate dance of existence. It is a constant that, rather than limiting our dreams of interstellar travel, deepens our appreciation for the profound and intricate laws that govern every moment of our being. The quiet elegance of the speed of light, defining the very fabric of our reality, is not merely a theoretical construct. It is a constant, rigorously tested and confirmed by countless observations and experiments throughout history. From the earliest inquisitive minds to the most sophisticated modern laboratories, humanity has sought to grasp the elusive nature of light, slowly uncovering its profound role as the universe's ultimate speed. Centuries ago, the prevailing wisdom held that light traveled instantaneously. It seemed to appear everywhere at once, an immediate presence. But even then, some thinkers dared to question this intuition. Galileo Galilei, in the early 1600s, attempted to measure its speed with lanterns on distant hills, though his methods were too crude to capture its immense velocity. It was the Danish astronomer Ole Romer in the late 1670s who first provided compelling evidence that light has a finite speed. By observing the irregular eclipses of Jupiter's moon Io, he noticed discrepancies that could only be explained if light took time to travel from Jupiter to Earth, depending on the planet's varying distances. His early estimate, though not entirely accurate by modern standards, was a monumental step, a quiet whisper that the universe's swift messenger was not infinitely fast. Later, in the mid-1800s, French physicists Hippolyte Fizeau and Léon Foucault, using ingenious laboratory setups involving rotating mirrors and toothed wheels, provided increasingly precise measurements, bringing the cosmic constant ever closer to its true value. These early efforts, a testament to human curiosity and ingenuity, laid the groundwork for a deeper understanding, transforming light from a mystical phenomenon into a measurable physical entity. The true theoretical understanding of light speed, however, emerged from the brilliant work of James Clerk Maxwell in the mid-1800s. He unified the seemingly disparate forces of electricity and magnetism into a single, elegant framework: Maxwell's equations. These four fundamental equations described how electric and magnetic fields generate and interact with each other. And within these equations, a profound prediction lay hidden: that disturbances in these fields propagate as waves, electromagnetic waves, and they would travel at a very specific, calculable speed. When Maxwell performed the calculations using known electrical and magnetic constants, the speed he derived was astonishingly close to the experimentally measured speed of light. This was not a coincidence. It revealed that light itself is an electromagnetic wave, a ripple in the invisible fields that permeate space. This realization was a quiet revolution, unveiling light, not as something that travels through a medium, but as a self-propagating vibration of fields, inherently possessing its constant velocity. It was a moment of profound unification, painting a picture of a universe where light is an intrinsic part of its electromagnetic tapestry. The advent of particle accelerators in the 20th century provided further highly rigorous confirmation of the speed of light limit and the relativistic effects it entails. In these colossal machines, particles such as protons and electrons are accelerated to speeds incredibly close to c, often reaching 99.9999% of light speed. Scientists observe directly how their mass increases dramatically, precisely as predicted by Einstein's equations. The particles become so heavy that further acceleration requires increasingly enormous amounts of energy, making it practically impossible to reach the absolute limit. Furthermore, the lifetimes of unstable particles, when accelerated to these relativistic speeds, are observed to stretch or dilate exactly as special relativity predicts. Muons, for instance, are subatomic particles with a very short natural lifespan. When created in our atmosphere by cosmic rays, they travel at near light speed. If time did not dilate for them, they would never reach the Earth's surface before decaying. Yet they do. Their extended lifetimes, precisely matching relativistic calculations, serve as a gentle, undeniable confirmation of time dilation. These experiments are not merely academic exercises. They are profound affirmations of the universe's fundamental rules, a continuous quiet whisper from the heart of matter itself. The constant speed of light, this cosmic bedrock, is not just a theoretical curiosity. It underpins many of the technologies that shape our modern world. Consider the Global Positioning System, or GPS. The satellites orbiting Earth transmit signals at the speed of light. For GPS to function with the incredible accuracy we rely on, providing precise location data, it must account for relativistic effects. The clocks on these satellites, moving rapidly relative to Earth and experiencing slightly weaker gravity, tick at a different rate than clocks on the ground. Without constant corrections based on both special and general relativity, the timing signals would drift, accumulating errors of many kilometers per day. Your car navigation, your smartphone's location services, all quietly depend on Einstein's profound insights into the nature of light and space-time. It's a subtle, invisible influence, a testament to how deeply the universe's fundamental laws are woven into the fabric of our daily lives, a serene harmony between cosmic constants and human innovation. Even our exploration of the cosmos, looking out at the distant galaxies through powerful telescopes, is fundamentally governed by this speed limit. Every image we capture, every spectrum we analyze, is a transmission from the past, limited by the time light has taken to reach us. This means that when astronomers study the most distant objects, they are essentially looking at the universe as it was in its infancy, billions of years ago. The speed of light acts as a cosmic time machine, allowing us to reconstruct the universe's history, piece by gentle piece. It is a profound gift, this finite speed, offering us a window into the origins of stars and galaxies, a chance to witness the universe's grand evolution. It teaches us patience, reminding us that the vastness of space is also a vastness of time, and that understanding the cosmos requires a quiet, reflective contemplation of its ancient light. Ultimately, the speed of light is more than just a measurement. It is a fundamental constant that defines the very essence of our universe. It dictates the interaction between mass and energy, shapes the flow of time and the perception of space, underpins our technology, and limits our observational reach. It is a constant that, in its unwavering nature, provides a stable, predictable framework for all physical phenomena. Rather than being a frustrating barrier, it is a source of profound wonder, revealing a universe of elegant laws and interconnected truths, a serene stage upon which the cosmic drama quietly unfolds. And in understanding this, we may find a deeper appreciation for the delicate balance that allows for the existence of everything, including ourselves, a brief conscious flicker within its boundless and beautifully constrained expanse. Implications of light's finite speed extend profoundly to our understanding of the universe's vastness and the limits of our knowledge. As we peer into the depths of the cosmos, every photon that touches our telescopes carries with it the story of a distant past. The light from the most remote galaxies has traveled for billions of years to reach us, meaning we are witnessing these celestial structures not as they are now, but as they were eons ago. This inherent delay creates what is known as the cosmic horizon, a boundary of information, a gentle veil beyond which the universe's current state remains a mystery to our instruments. It is not a physical wall, but a limit to what signals, what stories, have had enough time to arrive at our cosmic doorstep. This quiet truth means that the universe we observe is, in many ways, an ancient portrait, a collection of snapshots from different eras, arranged according to the travel time of light. We are, in a sense, each at the center of our own observable universe, a unique bubble of light-reachable reality, forever limited by the speed at which information can travel. This realization fosters a deep sense of humility and wonder, as it reminds us that much of the universe's grandeur, its ongoing present, unfolds beyond our capacity to perceive, a silent, continuous unfolding in the cosmic dark. This limitation also brings with it a profound sense of cosmic isolation. Because no information can travel faster than light, any civilizations in galaxies beyond our light cone, or even within it, but too far for two-way communication, are forever separated from us in a practical sense. A message sent across billions of light years might arrive long after the sender, or even their entire civilization, has ceased to exist. This vast cosmic silence, often referred to as the Fermi paradox in some contexts, is a direct consequence of the speed of light. It suggests that while the universe may be teeming with life, the sheer distances and the unyielding speed limit make meaningful real-time interaction an impossibility. This understanding can evoke our own brief flicker of consciousness, is a unique and precious phenomenon, unfolding within a vast, largely unreachable cosmic tapestry. It emphasizes the profound self-reliance of each pocket of life, each a solitary island of awareness in an ocean of light-speed-bound silence. The concept of a universal now is further dissolved by this understanding. Your now is a unique point in space-time, a personal slice of reality that shifts with your motion and gravitational context. For an observer on a distant exoplanet, what is happening for you right now might be their distant past or their far future. There is no absolute universal moment of now that binds all observers across the cosmos. This radical departure from our everyday intuition, first unveiled by Einstein, means that every individual, every planet, every star exists within its own local timeline, a unique rhythm dictated by the geometry of space-time around it. It's a gentle reminder of the subjective nature of our temporal experience, a tranquil thought that each of us is living our own unique sequence of moments, interwoven yet distinct within the grand four-dimensional block of space-time, while the speed of light stands as an unyielding constant for anything with mass. The human mind continues its serene quest for understanding, always probing the edges of the known. Theoretical physicists continue to explore concepts that, while not breaking the speed of light, might offer new perspectives on its nature or the universe's structure. Ideas such as tachyons, hypothetical particles that always travel faster than light, have been proposed. However, such particles would face their own set of profound challenges, including violating causality, making their existence highly problematic for our current understanding of physics. The exploration of such concepts is not an attempt to defy the fundamental limit, but rather a testament to the ongoing human drive to understand the universe in its entirety, to push the boundaries of what is conceivable within the elegant framework of physical laws. This quiet, persistent inquiry, even into the realm of the currently impossible, is a deep part of our scientific journey, a continuous meditative search for deeper truths. Ultimately, this cosmic limit, then, becomes a frame for our own fleeting existence, a gentle reminder that our conscious experience is a unique unfolding within an ancient, vast, and beautifully constrained cosmos. It is a boundary that, rather than diminishing our sense of possibility, deepens our appreciation for the intricate and harmonious speed of light, is a profound and beautiful truth, a constant that quietly ensures the coherence of the universe, allowing for the gentle dance of stars, galaxies, and life itself to unfold within its elegant bounds. It is a source of tranquil wonder, inviting us to reflect on our place within this grand, illuminated story. and our brief yet significant role in its ongoing narrative. As the echoes of these profound concepts gently recede, we are left with a tranquil understanding. Cosmic barrier, but a fundamental truth, a silent architect of our universe. It dictates the rhythm of space-time, shapes the very fabric of reality, and defines the horizons of our perception. This immutable constant ensures that the cosmos unfolds with a majestic coherence, a predictable dance of cause and effect. It is a source of deep wonder, reminding us that even within its boundless expanse, there are elegant, unwavering laws that govern all existence, from the smallest photon to the grandest galaxy. And as we drift into the quietude of the night, let us carry this serene thought, that we are all part of this astonishing, light-bound universe, our brief lives illuminated by the ancient, unwavering glow of its most fundamental constant. May these deep thoughts about the absolute limit of the universe carry you into a world of tranquil sleep. Remember that the universe is amazing and you are a part of it. Fall asleep with this feeling of serenity and endless knowledge. Good night. The question of what the universe is expanding into is one that often arises, conjuring images of a grand cosmic bubble stretching outward into some larger, empty void. Yet the reality, as revealed by the profound insights of modern cosmology, is far more subtle and, in its own way, even more astonishing. When we speak of the universe expanding, we are not talking about galaxies rushing through a pre-existing static space, as if they were shrapnel from an explosion. Instead, it is space itself that is expanding, growing and stretching, carrying the galaxies along with it. This distinction is crucial, for it means there is no edge to this expansion and no outside for the universe to fill. The universe, in this cosmological sense, is everything, and its expansion is the continuous creation of more space within itself. To truly grasp this, let us return to the familiar analogy of the surface of a balloon being inflated. Imagine tiny celestial bodies, like galaxies, drawn upon its two-dimensional surface. As the balloon expands, every drawn galaxy moves away from every other drawn galaxy. There is no central point on the surface from which they are all fleeing. Each galaxy observes all others receding from it, a uniform exodus driven not by their own motion across the surface, but by the stretching of the rubber itself. Now, this analogy is imperfect, as it represents a two-dimensional surface expanding into a third dimension. Our universe, however, is thought to be three-dimensional space, expanding into nothing external. It is the very fabric of our three-dimensional space that is stretching, not through some higher dimension, but intrinsically from within. This means that new space is simply coming into existence between gravitationally unbound objects, gently pushing them further apart. This profound understanding began to solidify in the 1920s, largely through the groundbreaking work of astronomers like Edwin Hubble. Observing distant galaxies, Hubble discovered a remarkable pattern. The farther away a galaxy was, the faster it appeared to recede from us. This relationship, now known as Hubble's law, was a pivotal moment in cosmology. The primary evidence for this recession comes from the phenomenon of redshift. As light from these distant celestial islands travels across the vast cosmic distances, the space it traverses expands. This stretching of space literally elongates the light waves themselves, increasing their wavelength and shifting them towards the red end of the electromagnetic spectrum, much like a siren's pitch drops as it moves away. This is not merely a Doppler effect caused by galaxies flying through space, but rather a direct consequence of the stretching of space itself. Further confirmation of this pervasive expansion comes from the cosmic microwave background radiation, the faint echo of the Big Bang, which permeates all of space and exhibits a uniform cooling over time, consistent with a universe that is steadily growing larger. One might then reasonably wonder, if everything is moving away from everything else, does that imply a center to this expansion, a point from which everything originated? Here again, our everyday intuition, honed by experiences within a static framework, can be profoundly misleading. The expansion of the universe has no identifiable center. Just as every point on the surface of an inflating balloon moves away from every other point without any single point being the center of the expansion, so too does every region of our universe experience this stretching of space. No matter where an observer is situated in the cosmos, they would witness the same universal outward flow, with distant galaxies receding from their vantage point in every direction. This concept is fundamental to the cosmological principle, which posits that the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same everywhere and in every direction. Such a universe, though potentially finite, has no edges and no privileged center, much like the surface of the Earth is finite but boundless. This dynamic view of space is deeply rooted in Albert Einstein's revolutionary theory of general relativity, which was published in 1915. Einstein's equations revealed that space and time are not separate, static entities, but are interwoven into a single, flexible fabric called space-time. This fabric is not a passive stage where cosmic events unfold. Rather, it is an active participant, capable of being warped and curved by the presence of mass and energy. The expansion of the universe is precisely this, a change in the geometry of space-time itself. It is not an event happening within space, but rather the evolution of space itself. It is the very structure of the cosmos that is changing, growing, weaving new distances between us and the most remote celestial islands. This means that when we look out into the night sky, we are not just observing objects in space, but witnessing the profound evolution of space itself, a silent, ceaseless unfolding that reshapes reality on the grandest scales. What then is driving this relentless expansion? For a long time, scientists assumed that the gravitational pull of all the matter in the universe would gradually slow down this expansion. However, in the late 1990s, astronomers made a startling discovery. The expansion of the universe is not slowing down, it is accelerating. Something is actively pushing space apart, causing it to stretch faster and faster. This mysterious force, or property of space, has been dubbed dark energy. While its exact nature remains one of the greatest puzzles in modern physics, current cosmological models suggest that dark energy makes up about 68% of the total energy density of the universe. It is a pervasive, repulsive force inherent to space itself, essentially causing more space to generate more dark energy, leading to an ever-increasing rate of expansion. This suggests that the void is not merely inert, but actively participating in the cosmic drama, a subtle yet powerful force shaping the destiny of everything. It is important to remember that this cosmic expansion is a large-scale phenomenon. We do not observe our bodies, our homes, our planet, or even our solar system stretching. This is because local gravitational forces and other fundamental interactions are overwhelmingly stronger than the expansive pull of dark energy on these smaller scales. Our galaxy, the Milky Way, and its immediate neighbors in the local group are gravitationally bound, meaning they are moving towards each other or orbiting a common center, unaffected by the overall expansion of the universe. The expansion only becomes evident when we observe structures that are not gravitationally bound to each other, such as distant galaxy clusters, where the stretching of space between them truly dominates their relative motion. Consider for a moment what this implies for your own existence, nestled within this vast and dynamic cosmos. You are a part of this expanding tapestry, a collection of atoms held together by forces that resist this universal stretching on local scales. While distant galaxies drift apart, your own being remains cohesive, a testament to the strength of the fundamental forces that govern matter. Yet the very space around you, in a subtle and immeasurable way, is also part of this grand unfolding. It is a profound reminder that our understanding of reality is constantly evolving, challenging our most basic assumptions about the nature of existence. What does it mean for our place in the cosmos to be part of something that is not just immense, but actively growing, moment by moment, without a true boundary or an external end. It evokes a sense of deep wonder, a quiet contemplation on the dynamic nature of everything we perceive and our fleeting yet significant presence within it. The universe is not merely expanding, it is an active, living entity, forever reshaping its own boundaries, and in doing so, it continually redefines our perception of its profound and infinite mystery. We have reflected upon the astonishing fact that the universe is not expanding into something, but rather that space itself is stretching, creating new distances between galaxies. This concept, so fundamental to our modern understanding, often challenges our intuitive grasp of reality. We are accustomed to thinking of expansion in terms of objects moving through a pre-existing container. But imagine, if you will, not a container, but the very canvas upon which all is painted, slowly, invisibly growing larger. This growth is a property of the cosmic fabric, the very geometry of space-time, and it means that for every unit of distance, more distance is being added. It is a continuous, gentle unfolding, an intrinsic property of the cosmos that does not require an external void to receive it. The universe in its entirety is the space, and its expansion is merely the increase of its own internal distances, a subtle yet profound act of self-generation that permeates every corner of its vastness. This is not a dramatic outward surge, but a pervasive, quiet stretching that happens everywhere at once, unseen by the casual eye, yet measurable by the most sensitive instruments. One of the deepest questions arising from this expansion concerns the ultimate geometry of our universe. Is it open, closed, or flat? These terms describe the overall curvature of space on the grandest scales, and each carries profound implications for its past, present, and future, as well as for the very nature of its boundlessness. A closed universe, much like the surface of a sphere, would be finite in extent, but boundless, allowing a journey in one direction to eventually return to the starting point. Its destiny, under the influence of gravity, would likely be a big crunch, where expansion reverses and all matter collapses back in on itself. In contrast, an open universe, akin to a saddle shape, would extend infinitely and expand forever, its curvature causing parallel lines to eventually diverge. A flat universe, conceptually like a vast, endless plane, also expands indefinitely, though at a decelerating rate, if not for the influence of dark energy. Here, parallel lines would always remain parallel. For decades, cosmologists have meticulously analyzed data to discern which of these geometries best describes our cosmos. The most compelling evidence comes from precise measurements of the cosmic microwave background radiation, the ancient light from the early universe. These observations, particularly those from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, reveal subtle temperature fluctuations in this background radiation. The angular size of these fluctuations acts as a cosmic ruler. If the universe were closed, these hot spots would appear larger than they are. If it were open, they would seem smaller. What we observe points overwhelmingly to a flat geometry. This means that parallel lines, if extended indefinitely, would remain parallel, and the sum of angles in a large triangle would precisely equal 180 degrees, just as in Euclidean geometry. This finding aligns beautifully with the theory of cosmic inflation, a period of extremely rapid expansion just fractions of a second after the Big Bang. Inflationary models naturally predict that the universe should be extraordinarily flat, smoothing out any initial curvature. It is as if a tiny, wrinkled region of space-time was stretched so dramatically that it became virtually flat on observable scales, much like a small bump on a balloon becomes imperceptible when the balloon is fully inflated. This elegant connection between the geometry of the universe and its earliest moments provides a profound anchor for our understanding of cosmic evolution. Yet, even if the universe is spatially infinite, our perception of it is limited. We speak of the observable universe, which is the spherical region of space from which light has had time to reach us since the Big Bang. This is not a boundary of the universe itself, but a boundary of our current observation. Imagine yourself at the center of a vast, ever-expanding sphere of light. Everything within that sphere is what you can potentially see. Beyond it lies the unobservable universe, regions from which light simply has not had enough time to travel to us, even at the incredible speed of light over the 13.8 billion years of cosmic history. This limit defines our cosmic horizon, a boundary of information rather than of physical space. It recedes from us as time progresses and light from ever more distant regions finally arrives. This means that the universe we perceive is a constantly growing sphere, but it is a sphere centered on us, the observer, and every other observer in the cosmos has their own unique observable universe, their own cosmic horizon stretching out around them. This realization can be both humbling and exhilarating. We are confined to our own cosmic window, able to glimpse only a fraction of what might truly exist. Yet, within this observable realm, there is an astounding immensity, a symphony of galaxies and structures that continues to inspire awe. To ponder the unobservable, the vast regions forever beyond our sight, is to acknowledge the profound mystery that still envelops us. It suggests that the true scale of existence might be far grander than our most ambitious measurements or theories can currently capture, reminding us of the endless depths of discovery that lie ahead, or perhaps forever out of reach, a quiet invitation to contemplate the boundless nature of reality itself. It reminds us that even with all our technological marvels, the universe holds secrets that may forever whisper just beyond our grasp, inviting a deep, tranquil contemplation of our place within its grand, expanding story. We have reflected upon the vastness of the observable universe and the profound mystery of the regions beyond our cosmic horizon. This boundary, defined by how far light has traveled to us over 13.8 billion years, reminds us that our perception is inherently limited, a fleeting snapshot of an ever-growing cosmic tapestry. Yet, even within this observable sphere, a deeper, more enigmatic force is at play, one that not only orchestrates the stretching of space, but accelerates its very expansion. This mysterious entity, which we call dark energy, represents perhaps the most profound puzzle in modern cosmology, shaping the ultimate destiny of everything we know. Dark energy is not a form of matter or radiation in the conventional sense. It does not clump together or interact with light. Instead, it appears to be an intrinsic property of space-time itself, a pervasive pressure that gently pushes the cosmos apart, causing the expansion to speed up rather than slow down under the influence of gravity. The discovery of this accelerated expansion in the late 1990s by independent teams of astronomers, including Saul Perlmutter, Adam Rees, and Brian Schmidt, came as a profound shock to the scientific community. They were studying distant supernovae, using them as standard candles to measure cosmic distances and the rate of expansion. The unexpected result was clear. The universe's expansion was not decelerating, as gravity would suggest, but was instead gaining momentum. This accelerating force aligns with a concept first introduced by Albert Einstein into his equations of general relativity: the cosmological constant. Initially, Einstein added this term to allow for a static universe, a notion he later famously called his biggest blunder after Hubble confirmed cosmic expansion. However, the cosmological constant, representing the energy density of empty space, now seems to be the most viable explanation for dark energy. It suggests that the vacuum of space is not truly empty, but possesses an inherent energy that exerts a repulsive gravitational effect. As space expands, more vacuum comes into existence, and thus more dark energy, leading to a self-reinforcing acceleration of the cosmic stretch. It is a subtle, constant hum of energy woven into the very fabric of existence, driving the universe towards an ever more diffuse future. The implications of this relentless acceleration are profound for the long-term fate of the universe. If dark energy continues to dominate, the most widely accepted scenario predicts a heat death of the universe. This is not a sudden, dramatic apocalypse, but a gradual, quiet descent into ultimate cold and emptiness. As space continues to expand and accelerate, galaxies that are not gravitationally bound to our own local group will recede beyond our cosmic horizon at an ever-increasing rate. Their light will become so stretched and faint, so redshifted, that it will eventually fade into an undetectable whisper. Over trillions of years, even the stars within galaxies will exhaust their fuel, collapsing into white dwarfs, neutron stars, and black holes. These remnants will eventually cool and evaporate, leaving behind a cosmos of ever-increasing emptiness, where the distances between any remaining particles become astronomically vast. Imagine a future far beyond human comprehension, where civilizations might gaze out into a night sky that is almost entirely dark, devoid of the luminous galaxies we see today. They would be isolated, trapped within their own gravitationally bound cluster, with no discernible evidence of the grand cosmic tapestry that once connected us all. The universe in their epoch would appear profoundly different, a testament to the ephemeral nature of our current, vibrant cosmic view. This cosmic isolation, though occurring on timescales that render it almost abstract, offers a profound reflection on the fleeting nature of our present cosmic window. We exist in a unique moment, a brief golden age where the universe is rich with observable structure, where light from billions of galaxies still reaches our telescopes. Our consciousness, our very ability to ask these questions about cosmic expansion and its destiny, exists within this precious, temporary epoch. To consider this deep future is to realize that our present view is a gift, a rare opportunity to witness a universe still teeming with light and wonder, before the slow, inexorable stretching of space potentially carries much of its grandeur beyond our reach forever. The cosmic journey we have undertaken, exploring the universe's expansion not into a void, but as the stretching of space itself, and contemplating its distant, quiet end, naturally leads us to reflect upon its dramatic beginning. For it is in the very first moments, just after the Big Bang, that the seeds of this expansion were sown, and the stage was set for the cosmos we inhabit. Our current understanding points to a period of astonishingly rapid growth known as cosmic inflation, a theoretical framework developed to resolve several perplexing questions about the universe's initial conditions. Imagine, if you will, the universe as an infinitesimally small, incredibly dense point, brimming with unfathomable energy. Then, in an instant, a burst of exponential expansion occurred. This was not the gradual stretching we observe today, but a superluminal acceleration where space itself expanded faster than the speed of light. Such a concept, while challenging to visualize, is permitted by the laws of physics, as it is space, not matter moving through space, that undergoes this rapid inflation. This period, lasting for only a tiny fraction of a second, just 100 trillionth of a second, effectively smoothed out any initial irregularities, making the universe remarkably uniform and flat on large scales, much like inflating a tiny crumpled piece of paper to an immense size would make its surface appear perfectly smooth and flat. This elegant solution addresses what cosmologists refer to as the flatness problem and the horizon problem, explaining why distant regions of the universe, too far apart to have ever interacted since the Big Bang, nonetheless exhibit such similar temperatures in the cosmic microwave background. This theory of cosmic inflation, first proposed by Alan Guth in 1980, is more than a clever mathematical trick. It is supported by the subtle patterns observed in the cosmic microwave background. The minute variations in temperature within this ancient radiation, meticulously mapped by instruments like the Planck satellite, are precisely what inflation predicts. Quantum fluctuations in the very early universe, stretched to cosmic scales by the rapid expansion, forming the primordial seeds for the vast structures of galaxies and galaxy clusters we see today. It is a profound thought that the largest structures in the universe, the colossal webs of galaxies stretching across millions of light years, may owe their existence to quantum jitters on the smallest conceivable scales, magnified into cosmic reality. This transformation of quantum uncertainty into cosmic architecture offers a truly humbling perspective on the interconnectedness of all scales of existence. But the theory of inflation holds an even more radical implication for our understanding of cosmic expansion, the possibility of a multiverse. In some inflationary models, the process of inflation might not have ended uniformly everywhere. Instead, it could be an eternal phenomenon, continuing indefinitely in vast regions of a larger meta-universe, while in localized pockets like our own, inflation ceases, giving birth to separate bubble universes. Each of these bubbles would then expand and evolve according to its own initial conditions and fundamental physical laws. Our universe in this grander cosmic landscape would simply be one bubble among an infinite or near infinite ensemble of other universes, each perhaps vastly different from our own, with varying constants, different types of particles, or even entirely distinct dimensions. This concept profoundly shifts our perspective on what the universe is expanding into. It suggests that our universe is not expanding into an external void of nothingness, but rather into a continually inflating metaspace that is simultaneously giving rise to countless other universes. It is as if the cosmic expansion we observe is a local manifestation of a much larger ongoing process of universal generation. This eternal inflation theory implies that the universe, in its broadest sense, is an ever-birthing entity, an endless factory of realities, each unfolding according to its own unique cosmic narrative. Such a vast and intricate tapestry of existence, where our universe is but one thread, invites a deep sense of philosophical contemplation. Are the fundamental laws and constants of our universe merely arbitrary selections from an infinite array of possibilities, fine-tuned by chance for the emergence of life and consciousness? Or is there a deeper principle that favors universes like ours? While these questions remain largely in the realm of theoretical physics and philosophy, the very possibility of a multiverse challenges our anthropocentric view, urging us to consider our place not just within one universe, but within an unimaginably diverse cosmic ensemble. It offers a tranquil yet profound shift in perspective, transforming our sense of isolation into a feeling of belonging within an infinitely grander, perpetually expanding cosmic story, where your conscious awareness is a fleeting, precious glimpse into one tiny yet magnificent corner of reality's boundless unfolding. We have ventured into the realm of the multiverse, where our universe might be but one of countless cosmic bubbles, each with its own laws, all expanding within a grander, eternally inflating metaspace. This profound revelation naturally leads us to a deeper inquiry. What is this space that expands, that stretches and grows? What is its most fundamental nature beneath the familiar three dimensions we perceive, interwoven with time into space-time? Our most successful theories of the cosmos, general relativity and quantum mechanics, describe reality with breathtaking precision, yet they speak in different languages, particularly when it comes to the very fabric of existence at its most extreme scales. General relativity paints space-time as a smooth, continuous, and dynamic sheet, bending and flowing under the influence of matter and energy. Quantum mechanics, on the other hand, reveals a universe built from discrete, quantized packets of energy and information. When we attempt to merge these two pillars of physics into a single, unified theory of quantum gravity, the very notion of continuous space-time begins to dissolve, hinting that space itself might not be fundamental, but rather an emergent phenomenon, much like the smooth surface of an ocean emerges from countless individual water molecules. This is the frontier of theoretical physics, where our most cherished assumptions about reality are gently but firmly questioned, pushing the boundaries of our cosmic understanding into realms of profound abstraction. Consider, for a moment, the profound implications of such a perspective. If space is not an infinitely divisible continuum, but rather composed of discrete, irreducible units, like tiny fundamental grains, then its expansion takes on a profoundly different character. It would not be the stretching of an already smooth canvas, but rather the continuous addition of these elementary spatial atoms. One prominent contender for a theory of quantum gravity is loop quantum gravity, a framework that proposes that space-time is quantized, woven from an intricate network of minuscule loops, far smaller than anything we can currently detect, existing at the Planck scale, which is roughly 10 to the power of minus 35 meters. In this view, space is fundamentally granular, a kind of cosmic weave, not unlike a digital image appearing smooth from a distance, but revealing individual pixels upon closer inspection. The expansion of the universe, then, could be interpreted as the growth of this network, the generation of more fundamental loops, effectively adding new pixels to the cosmic image. This is a subtle, yet powerful reinterpretation of expansion, suggesting that the universe is not pushing into anything external, but rather generating more of its own intrinsic components. It is a quiet, ceaseless act of self-construction, a continuous unfolding of reality from its most elemental constituents. This perspective offers a profound sense of self-sufficiency for the universe, an entity that expands by creating more of its own substance, rather than merely occupying more of an external container. It transforms the perceived emptiness into a dynamic, generative medium, a quiet engine of cosmic creativity. Another theoretical avenue, string theory, offers a different, yet equally radical vision of space-time's origins. In this framework, the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating one-dimensional strings. The different vibrations of these strings give rise to all the various particles and forces we observe. Crucially, string theory often requires the existence of extra spatial dimensions, typically 10 or 11 in total, which are curled up or compactified into incredibly small scales, rendering them imperceptible to us in our everyday experience. From this perspective, our familiar four-dimensional space-time, including its expansion, could be an emergent phenomenon, a projection or a lower-dimensional manifestation of these higher-dimensional dynamics. The expansion of our three spatial dimensions might then be linked to the unfolding or stretching of these hidden dimensions, or perhaps the way these fundamental strings interact and organize themselves to create the illusion of a continuous, expanding space. This is a concept that echoes the holographic principle we sometimes discuss, where a three-dimensional reality might be encoded on a two-dimensional boundary, implying that our perceived reality is a kind of projection from a deeper, more complex substrate. In this view, the universe isn't expanding into anything in the conventional sense, but rather its dimensionality is being revealed or further manifested from an underlying higher dimensional reality. A silent, elegant dance of fundamental strings, creating the vastness we observe, a symphony of vibrations. The very fabric of our perceived reality, then, could be a mere shadow cast by these unseen, intricate dances. These are not mere philosophical musings, but active areas of scientific research, seeking to bridge the chasm between the very large and the very small to understand the universe at its most foundational level. The immense challenge lies in reconciling the smooth, macroscopic geometry of general relativity, which describes gravity as the curvature of space-time, with the turbulent, probabilistic nature of quantum mechanics, which governs particles at the Planck scale. This quest is to uncover the ultimate building blocks of reality and to comprehend precisely how they give rise to the space-time we inhabit and the expansion we measure. These theories push the boundaries of our imagination, suggesting that empty space is anything but empty. It is a vibrant quantum foam, constantly bubbling with virtual particles and latent energy, a dynamic substrate from which everything, including the very expansion itself, arises. This fundamental reevaluation of the vacuum of space is central to understanding what the universe is truly expanding from and how it continues to grow. While still speculative, these theories invite us to consider that the nature of space and time, the very stage upon which our lives unfold, might be far more ephemeral and dynamic than we instinctively believe. Our everyday experience of a solid, unchanging ground beneath our feet and a steady flow of time is a macroscopic approximation, a simplification of a far more intricate and fluctuating quantum reality. The expansion of the universe, when viewed through the lens of quantum gravity, becomes a question not just of scale, but of fundamental ontology. Is the universe expanding by adding more fundamental units of space, or by revealing more of its inherent, higher dimensional structure? This shift in perspective from space as an empty container to space as a dynamic, emergent entity is a cornerstone of our evolving cosmic narrative, prompting us to rethink the very definition of nothingness and its profound active role in the cosmos. And when we consider this, it shifts our perspective on ourselves in a subtle yet profound way. You, listening now, are a complex pattern of particles and fields intricately woven into the fabric of this expanding cosmos. Your very existence, your thoughts, your consciousness are intimately connected to the fundamental laws that govern the universe's origin and its ongoing evolution. If space is emergent, if reality is granular at its core, then your own sense of being, of having a fixed location in an expanding cosmos, is a beautiful, intricate dance of these fundamental constituents. It is a quiet invitation to ponder that perhaps your own personal space, the space of your immediate surroundings, is also, in its own way, a localized manifestation of this grand cosmic stretching. It is a space that feels solid and stable, yet is subtly influenced by the very same expansion that separates galaxies. This deep connection reminds us that we are not passive observers of the universe, but active participants, our very being echoing the grand processes of creation and expansion. This realization can bring a deep sense of calm, an understanding that even in our smallest moments, we are part of something infinitely vast and perpetually unfolding, a silent, graceful dance of existence. We have pondered the profound implications of space itself being an emergent, perhaps even granular phenomenon, rather than an inert, continuous backdrop. This leads us to question the very nature of what we colloquially call empty space, or the vacuum. Our intuition often perceives a void as simply the absence of anything at all. No matter, no light, no energy. Yet, at the most fundamental levels of reality, as described by quantum field theory, such absolute emptiness does not exist. The quantum vacuum is, in fact, a vibrant, restless sea of activity, a dynamic medium constantly teeming with fleeting energy fluctuations. Imagine, if you will, not a serene, still pond, but a deep, dark ocean, where even in its calmest depths, countless bubbles spontaneously form and vanish in a ceaseless dance. These bubbles are analogous to what physicists call virtual particles, pairs of particles and antiparticles that momentarily pop into existence from the vacuum's inherent energy, only to almost immediately annihilate each other, returning their borrowed energy to the quantum field. This phenomenon is not merely theoretical speculation, its effects are measurable. The Casimir effect, for instance, demonstrates that two uncharged parallel metal plates placed extremely close together in a vacuum will experience a tiny attractive force. This force arises because the fluctuating quantum fields between the plates are constrained, allowing fewer virtual particles to exist there compared to the unconstrained space outside, creating an imbalance in vacuum pressure that gently pushes the plates together. This extraordinary observation confirms that even in the deepest void, there is a tangible, energetic presence. This inherent energy of the quantum vacuum is, in essence, the leading candidate for the mysterious dark energy that drives the accelerating expansion of our universe. It suggests that space itself possesses an intrinsic energy density, a pervasive pressure that acts as a form of anti-gravity, gently pushing galaxies further apart. As the universe expands, more space comes into being, and with it, more of this vacuum energy. This creates a self-sustaining cycle. The expansion generates more dark energy, which in turn drives further, faster expansion. It is a cosmic engine powered by the very fabric of nothingness, continuously generating more of itself. This is why the universe is not expanding into something external. It is expanding by creating more of itself from within, powered by the latent energy of the quantum vacuum. The implications of this vacuum energy are not limited to the distant future of the cosmos. They extend back to its very beginning. During the period of cosmic inflation, it is believed that a much more potent form of vacuum energy temporarily dominated the universe, driving its hyper-rapid exponential expansion. This primordial vacuum energy stretched the nascent cosmos to unimaginable scales, smoothing out any initial irregularities and setting the stage for the homogeneous, flat universe we observe today. Even after inflation ended, a residual, much weaker form of this vacuum energy persisted, which we now identify as the dark energy accelerating the universe's current expansion. Thus, the expansion we witness today is a direct descendant of the explosive growth that shaped the very earliest moments of reality. This understanding profoundly reshapes our concept of the cosmic void. It is no longer a passive emptiness waiting to be filled, but an active, energetic medium, a dynamic source of creation and propulsion. The universe's expansion is not a movement through a pre-existing container, but rather the continuous generation of new space, new distances, woven into the fabric of reality by this ceaseless quantum activity. It is a universe that is not merely growing larger, but perpetually renewing and creating its own dimensions from within. Consider this profound dance of creation and expansion, this subtle hum of energy that underlies everything. Your own awareness, your very existence, unfolds within this dynamic, self-generating cosmos. The space around you, seemingly static and familiar, is a part of this grand, ongoing process, a localized manifestation of the universe's intrinsic energy. Peace, a quiet understanding that you are not separate from the vast cosmic unfolding, but intimately connected to its most fundamental rhythms. It invites a contemplative awareness that even in the stillness of your quiet surroundings, the universe is actively expanding, creating more of its wondrous self, and in that silent, majestic process, you're an integral, conscious participant. This cosmic embrace offers a tranquil reassurance, a gentle reminder that your place in the universe is not merely observed, but deeply woven into its very essence, a fleeting yet eternal pattern in the boundless dance of existence. We have just considered the profound implications of the quantum vacuum, a restless sea of energy that may well be the dark energy driving the accelerated expansion of our universe. This invisible force, inherent to space itself, is gently but relentlessly pushing all gravitationally unbound structures further and further apart. This acceleration means something quite remarkable for our cosmic future, and indeed for our present perception. It implies the existence of a cosmic event horizon, a boundary far more profound than the mere edge of our observable universe. To truly grasp this concept, let us consider a more detailed distinction. The particle horizon defines the limit of what we can currently observe. It is the maximum distance from which light, emitted since the Big Bang, has had sufficient time to reach us. This horizon is ever expanding, as each passing moment allows light from slightly more distant regions to finally arrive at our telescopes, gradually revealing new celestial wonders. However, the cosmic event horizon presents a different, more absolute kind of limit, one dictated by the accelerating nature of the universe's expansion. Due to dark energy's persistent push, there are galaxies so distant that light emitted from them today, even if traveling at the ultimate speed limit of the cosmos, will never reach us. The space between us and those galaxies is expanding so rapidly and will continue to accelerate its stretching that any light signal attempting to bridge the gap will be forever carried away by the expanding fabric of space-time, unable to ever reach us. This is a concept that challenges our everyday understanding of distance and speed. We are accustomed to thinking of objects moving through space and thus being constrained by the cosmic speed limit of light. Yet here, it is space itself that is expanding. Imagine 2 points on a stretching rubber sheet. The points themselves are not moving on the sheet, but the sheet itself is growing, increasing the distance between them. If the sheet stretches fast enough, 2 very distant points can effectively recede from each other at a rate greater than the speed of light, not because they are moving through space faster than light, but because new space is being created between them. This is precisely what happens in the universe on cosmological scales. Distant galaxies appear to recede from us at speeds greater than the speed of light, not violating Einstein's theory of special relativity, because it is the expansion of space, not the motion of objects through space, that is responsible. The rate of this cosmic stretching is quantified by the Hubble parameter, often referred to as the Hubble constant, though it is not truly constant but changes over cosmological time. Its value reflects how quickly the universe is expanding at any given moment. Current measurements, primarily from observations of the cosmic microwave background and distant supernovae, suggest a value that indicates the universe is expanding by about 70 kilometers per second for every 3.26 million light-years of distance. However, a fascinating puzzle in modern cosmology, known as the Hubble tension, highlights a discrepancy. Different measurement techniques yield slightly different values for this expansion rate, hinting at either new physics beyond our current models or subtle systematic errors in our observations. This scientific mystery underscores that our understanding of cosmic expansion is still evolving, a testament to the dynamic nature of scientific inquiry. To further clarify how we measure and conceptualize these immense cosmic distances in an expanding universe, cosmologists use 2 key terms: co-moving distance and proper distance. Co-moving distance essentially refers to a coordinate system that expands along with the universe. Imagine a fixed grid laid across the cosmos. Galaxies might move slightly within their local clusters, but their co-moving coordinates remain relatively stable. Proper distance, on the other hand, is the distance between 2 points as measured by a ruler at a specific moment in cosmic time. As the universe expands, the proper distance between 2 co-moving points increases. So, while the co-moving distance to a distant galaxy remains constant, its proper distance from us continually grows due to the stretching of space. This means that a galaxy that is now, in terms of proper distance, 46 billion light-years away, was much closer in the past, even though its co-moving coordinates have not changed. The existence of a cosmic event horizon driven by dark energy means that there will come a time when all galaxies outside our local group will have receded beyond our ability to ever observe them, even in principle. Their light will simply be unable to overcome the accelerating expansion of the intervening space. This is a profound form of cosmic isolation. Future civilizations, billions of years from now, might gaze upon a night sky almost entirely empty of external galaxies, having no direct knowledge of the vast interconnected cosmos that we currently perceive. Their observable universe would shrink to encompass only their immediate galactic neighborhood. This thought, while perhaps a touch melancholic, also offers a deep, quiet sense of wonder about our fleeting moment in cosmic time. We are privileged to live in an era that paints our skies and fills our telescopes. Our ability to map the cosmos, to study its expansion, and to even conceive of its ultimate fate is a unique gift of our epoch. It is a reminder that our understanding is a temporary window into an eternal process, a brief period of clarity before the cosmic veil of accelerating expansion gradually descends, obscuring the distant tapestry of existence. To contemplate this is to find a tranquil appreciation for the present, for the light that still reaches us, and for the profound interconnectedness we share with a universe that is forever expanding, forever unfolding its mysteries, inviting us to simply be present in its grand, silent dance. We have contemplated the profound cosmic event horizon, a boundary from which light emitted today will never reach us, a testament to the accelerating expansion of space itself. This acceleration, as we know, is attributed to dark energy, a mysterious component that constitutes roughly 68% of the universe's total energy density. Yet, despite its overwhelming influence on the cosmos, dark energy remains one of the most enigmatic entities in modern physics, a profound puzzle that challenges our deepest understanding of reality. It is not a force in the conventional sense, pulling or pushing on individual objects, but rather an inherent property of space itself, a pervasive pressure woven into the very fabric of space-time that causes it to stretch. The most straightforward explanation for dark energy is a reintroduction of Einstein's cosmological constant, a term he initially conceived to maintain a static universe. This constant suggests that even empty space possesses an intrinsic, non-zero energy density, which, unlike matter or radiation, does not dilute as the universe expands. Instead, as new space is created, more of this vacuum energy simply comes into existence, maintaining a constant energy density across the cosmos. This constant density of repulsive energy ensures that the acceleration of expansion continues unabated. However, the theoretical value predicted for this vacuum energy by quantum field theory is astronomically larger than what astronomers actually observe, by a staggering factor of about 120 orders of magnitude. This immense discrepancy, often referred to as the cosmological constant problem, is arguably the greatest unsolved mystery in physics, suggesting that our understanding of the quantum vacuum, or gravity, or both, is fundamentally incomplete. This profound fine-tuning problem leads scientists to explore alternative theories for dark energy. One such theory proposes quintessence, a dynamic, evolving energy field that permeates space. Unlike the cosmological constant, which is fixed, quintessence could change over time, its properties varying throughout cosmic history. Such a dynamic field might offer a more nuanced explanation for the observed acceleration, potentially allowing for different future scenarios for the universe, beyond a simple heat death. Perhaps this field would eventually decay, or its repulsive nature might strengthen further, leading to even more extreme cosmic fates. While no direct evidence for quintessence has yet been found, the concept highlights the ongoing intellectual quest to comprehend the fundamental nature of this cosmic accelerator. It is a testament to the ingenuity of theoretical physicists who continue to craft elegant mathematical frameworks in an attempt to capture the elusive essence of the universe's most dominant, yet unseen, component. The very existence of dark energy forces us to reconsider the fundamental constituents of our universe. Our familiar world of stars, planets, and galaxies made of ordinary matter comprises only about 5% of the cosmos. Dark matter, another invisible component, accounts for roughly 27%, providing the gravitational scaffolding that holds galaxies and galaxy clusters together. The remaining 68% is dark energy. This means that nearly 95% of the universe is composed of entities we cannot directly observe, and whose nature we do not fully understand. We are, in essence, living in a cosmos dominated by shadows, guided by forces that remain largely hidden. This realization can evoke a sense of quiet humility, reminding us of the vast expanse of knowledge yet to be uncovered, a silent invitation to continue our scientific exploration. The accelerating expansion, driven by dark energy, also has profound implications for the future of scientific discovery itself. As distant galaxies recede beyond our cosmic event horizon, their light will eventually become undetectable, effectively isolating our local group of galaxies from the rest of the universe. Future astronomers, billions of years from now, might observe a largely empty sky, leading them to fundamentally different conclusions about the universe's origins and its composition. They might never know of the billions of galaxies that once populated the observable cosmos, or even the evidence for the Big Bang itself, as the cosmic microwave background radiation would also be redshifted beyond detection. This thought is a powerful reminder of the unique, temporary window of observation we currently inhabit, a privileged moment in cosmic history where the universe's grand narrative is still largely accessible to us. And as you reflect upon this cosmic dance, this interplay of visible matter, unseen dark matter, and the pervasive, accelerating push of dark energy, consider your own place within it. Your physical being, your consciousness, exists within this intricate balance of forces on a planet orbiting a star in a galaxy that, for now, remains gravitationally bound. The very fact that you are capable of contemplating these profound mysteries, of asking, what is the universe expanding into, is a remarkable consequence of cosmic evolution. You are a conscious manifestation of this universe, a temporary arrangement of atoms that has, for a brief epoch, the capacity to observe and wonder at its own grand, expanding story. This awareness can bring a tranquil sense of connection, a feeling of being an integral part of this vast, dynamic, and endlessly mysterious cosmos, gently drifting towards sleep with the quiet hum of the universe's expansion as a lullaby. Cosmic event horizon, a boundary that will ultimately sever our ability to observe distant galaxies due to the relentless, accelerating expansion of space itself, driven by dark energy. This concept, so deeply rooted in the physics of our universe, leads us to a fascinating and perhaps melancholic reflection on the impermanence of our cosmic view and the very nature of information across vast stretches of time. For our descendants, billions, even trillions of years into the future, the night sky will appear profoundly different, a testament to the dynamic evolution of reality. Imagine a time far, far from now when the light from galaxies beyond our local group has been stretched into oblivion, redshifted past any hope of detection. Our galactic neighborhood, including the Milky Way and Andromeda, will have merged into a single, colossal galaxy, a lonely island in an otherwise vast, dark ocean of expanding space. Future astronomers, if they exist, would gaze out into an almost entirely empty cosmos. The evidence for the Big Bang itself, the cosmic microwave background radiation, would also have been stretched to such extreme wavelengths that it too would be undetectable, fading into an unrecoverable whisper. They would have no direct observational proof of a universe teeming with billions of other galaxies, nor the telltale relic radiation of its fiery birth. Their cosmological models would be built upon a much smaller, more isolated universe, potentially leading to radically different conclusions about its origin, its size, and its ultimate fate. This slow erasure of cosmic history is a profound consequence of space's accelerating stretch, a testament to the fact that even information, in a sense, can be lost to the cosmic currents. This unfolding cosmic isolation invites us to appreciate the unique temporal window in which we currently exist. We are living in a privileged epoch, a fleeting moment in the universe's 13.8 billion-year history, where the light from countless galaxies, stretching back almost to the Big Bang, is still accessible to our telescopes. We can observe the early universe, witness the formation of the first stars and galaxies, and trace the evolution of cosmic structure. This ability to piece together the grand narrative of the cosmos, from its inflationary birth to its accelerating present, is a rare opportunity that will not be available to all future sentient beings. Our current understanding of the universe's expansion, its geometry, and the mysteries of dark energy and dark matter is a product of this fortunate observational vantage point. The very concept of now also takes on a more complex meaning in an expanding universe. In our everyday lives, we intuitively understand a shared present moment, a universal now that applies to everyone simultaneously. However, Albert Einstein's theory of relativity taught us that simultaneity is relative. What one observer perceives as simultaneous, another in a different state of motion might see as occurring at different times. In a universe where space itself is stretching, this relativity is amplified. The expansion means that the cosmic clock ticks differently across vast distances, influenced by the local curvature of space-time and the global expansion. There is no single, absolute cosmic present that encompasses all events across the entire universe. Each observer experiences their own now, a localized slice of space-time that shifts and tilts depending on their position and motion within the expanding cosmic fabric. This personal relative nature of time, intricately linked to the expansion of space, reminds us that our individual experience of reality is deeply interwoven with the universe's grand dynamics. And as you consider this profound relativity, this unique window of observation, and the eventual isolation that awaits future cosmic inhabitants, perhaps a sense of tranquil wonder settles upon you. You are, at this very moment, a conscious participant in the universe's ongoing story, a brief but brilliant flicker of awareness within its boundless, expanding expanse. The questions you ask, the knowledge you seek, are part of the universe's own journey of self-discovery. The expansion of space, driven by dark energy, is not merely a distant physical phenomenon. It is an intimate part of your reality, shaping the very limits of what can be known and seen. This profound realization of our transient yet deeply connected place within the cosmic unfolding can offer a quiet sense of peace, a gentle invitation to let go of the need for absolute certainty, and instead embrace the beautiful, expanding mystery of existence itself as you drift towards a restful sleep. As we gently draw our reflections to a close, having traversed the boundless concepts of cosmic expansion and the profound limits of our perception, we are left with a sense of quiet awe. The universe, in its majestic unfolding, is a testament to change, to growth not into an external void, but from within its own intricate fabric. We have contemplated the invisible hand of dark energy, steadily accelerating the cosmic dance, gradually isolating future observers within their lonely galactic islands. Yet this very realization imbues our present moment with an extraordinary significance. We exist in an epoch where the echoes of the Big Bang still resonate, where the light from countless distant galaxies continues to paint our night skies with stories from across billions of years. We are given the rare gift of witnessing the universe in its vibrant maturity, a period of rich, accessible information before the cosmic event horizon inexorably draws its veil. In this quiet understanding, we might find a deep sense of peace. The universe does not demand our comprehension of every secret, but rather invites our contemplation of its boundless mysteries. You, a conscious part of this grand, expanding tapestry, are a fleeting yet precious arrangement of cosmic elements capable of asking these profound questions. Your own being reflects the dynamic, ever-changing nature of all existence. So, let these thoughts of endlessly stretching space, of hidden energies, and of our unique place in this cosmic story gently settle within you. May these deep thoughts about the universe's ceaseless expansion carry you into a world of tranquil sleep. Remember that the cosmos is an ever-unfolding wonder, and you are an intrinsic, beautiful part of its magnificent journey. Fall asleep with this feeling of serenity and endless knowledge. Good night. Good evening, and welcome to Physic for Sleep. Tonight we embark on an intellectual journey, exploring the intriguing thought experiment of Maxwell's demon, a subtle challenge to the very fabric of entropy and the perceived arrow of time. Before we gently immerse ourselves in the profound implications of thermodynamics and the nature of information, I would like to know where you are at this moment. Perhaps you are settled in an armchair by the fireplace as rain falls outside, or lying in your bedroom, gazing at the stars through the window. Let this cozy setting be your anchor as we unhurriedly wander through the subtle paradoxes of physical law. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin Our journey tonight begins with a quiet contemplation of one of the most fundamental principles governing our universe, the second law of thermodynamics. This law, in its essence, states that the total entropy of an isolated system can only increase over time or remain constant in ideal cases. What does this truly mean for us, for the cosmos, and for our own experience of existence? Simply put, entropy can be understood as a measure of disorder, or more precisely, the dispersal of energy within a system. It describes the universe's relentless, unhurried march towards a state of equilibrium, a uniform distribution of energy where no further work can be extracted. Imagine a drop of ink gently released into a clear glass of water. At first, the ink is concentrated, distinct, but given time, it will inevitably spread, diffusing through the water until the entire glass is a uniform, pale hue. This spreading, this loss of distinction, is an increase in entropy. Or consider a hot cup of tea left on a table. Its heat will gradually dissipate into the cooler room until both are at the same temperature. This natural progression from order to disorder, from concentrated energy to dispersed energy, is observed everywhere, from the cooling of stars to the fading of memories, defining what we often perceive as the unidirectional flow of time. It suggests that the universe, left to its own devices, tends towards a state of maximum disorder, a cosmic sameness, often referred to as heat death. It was in this context, in 1867, that the brilliant Scottish physicist James Clerk Maxwell, known for his groundbreaking work on electromagnetism, conceived a curious thought experiment. He envisioned a tiny, intelligent being, a demon as it came to be known, guarding a small door between two chambers filled with gas molecules at an identical temperature. In such a system, molecules are constantly moving, colliding, and exchanging energy. Some move faster, possessing more kinetic energy, while others move slower. The chambers are initially in thermal equilibrium, meaning the average kinetic energy of the molecules is the same on both sides, and thus the temperature is uniform. Now, Maxwell's ingenious demon, with its perfect observational capabilities, watches these molecules approaching the door. When a fast-moving molecule approaches from the left, heading towards the right chamber, the demon quickly opens the door, allowing it to pass through. Conversely, when a slow-moving molecule approaches from the right, moving towards the left chamber, the demon opens the door for it. All other molecules are simply blocked. By carefully and selectively opening and closing the door without expending any macroscopic work, the demon begins to sort the molecules. Over time, the right chamber accumulates faster, hotter molecules, while the left chamber becomes home to slower, colder ones. What Maxwell proposed through this seemingly simple sorting was a direct challenge to the second law of thermodynamics. The demon appears to create a temperature difference between the two chambers, thus decreasing the overall entropy of the system. It has, in effect, spontaneously created order out of disorder, concentrating energy in one chamber and diminishing it in the other, all without any apparent energy input. This would mean that the heat from the hotter chamber could then be used to perform work or to run an engine, effectively creating a perpetual motion machine of the second kind, a device that extracts work from a single heat reservoir, a feat explicitly forbidden by the second law. The paradox of Maxwell's demon troubled physicists for decades, for if such a demon could exist, the fundamental arrow of time, the irreversible trend towards increasing entropy, would be undermined. It suggested a loophole, a way for intelligence and information to seemingly defy the very laws that govern the natural world's progression. If order could be created from disorder without cost, then perhaps the ultimate fate of the universe, its eventual heat death, was not so inevitable after all. This thought experiment forced scientists to look deeper into the nature of information itself and its intimate connection to energy and entropy. The demon's ability to see and decide implies a process of acquiring and processing information, and it is in this subtle act of observation and memory that the resolution to the paradox eventually emerged. The very act of discerning between fast and slow molecules, of storing and processing that information, it turns out, has an entropic cost, a price that must be paid in the currency of the universe's fundamental tendency towards disorder. This is not merely a philosophical musing, but a profound physical truth that reminds us how deeply intertwined the concepts of energy, information, and time truly are, shaping not only the grand cosmic narrative, but also the minutiae of our own conscious experience. The key to unraveling Maxwell's paradox arrived not from refining our understanding of heat and work, but from a deeper dive into the physics of information itself. Decades after Maxwell's initial thought, in 1929, Leo Szilard proposed that the demon's act of measurement, the very process of distinguishing between fast and slow particles, must inherently involve an increase in entropy. He argued that the demon needed to acquire information about each molecule's velocity, and this act of gaining knowledge could not be performed without some thermodynamic cost. Later, in 1951, Léon Brillouin elaborated on this, suggesting that the demon would need a source of light to see the molecules, and the photons used for this illumination would carry energy, ultimately increasing the system's entropy. While these insights were crucial steps, they didn't quite close the door on the demon entirely. The demon could, in theory, use very little energy for each observation. The true resolution came with the work of Rolf Landauer in 1961, who shifted the focus from the act of measurement to the act of erasure. Landauer's principle posits that the irreversible erasure of information necessarily generates a minimum amount of heat, and thus increases entropy in the environment. Imagine the demon's internal memory as a series of tiny bits, each recording whether a molecule was fast or slow. To operate continuously, sorting countless molecules, the demon's memory would eventually fill up. It would then need to erase this old information to make room for new data. This act of resetting a memory bit from a definite state, 0 or 1, to a default, undefined state, like a blank slate, is an irreversible process. Think of it as tidying up a desk. To clear space for new work, you must take the old papers and dispose of them, a process that requires effort and energy, even if minimal. Landauer showed that for every single bit of information erased, at least k sub bt natural logarithm of 2 of energy must be dissipated as heat into the environment, where k sub b is Boltzmann's constant and T is the absolute temperature. This seemingly small amount of energy, when multiplied by the vast number of decisions the demon would make over time, accounts for the entropy reduction it seemingly achieves. The demon's internal operations, its very act of thinking and remembering, prevent it from ever truly violating the second law. It's a subtle but profound balancing act. The order created by sorting is precisely compensated by the disorder generated in the demon's own internal bookkeeping. This means that intelligence, even at its most fundamental, cannot escape the thermodynamic laws of the universe. Any entity that processes information, whether it be Maxwell's demon, a living organism, or a sophisticated computer, must ultimately pay an entropic price for its operations. The act of acquiring, storing, and especially erasing information inevitably contributes to the overall increase in the universe's disorder. It's a beautiful demonstration of how deeply interwoven the abstract world of information is with the physical reality of energy and entropy. The arrow of time, the relentless progression towards equilibrium, remains unbroken. Our own minds, in their intricate dance of thought and memory, are also subject to these same physical constraints. Every new memory formed, every old one discarded, is a process that, at its core, involves the manipulation of physical states, tiny changes that collectively echo the broader cosmic tendency. So, when you drift towards sleep, perhaps consider the quiet, tireless work your own brain is performing, organizing and clearing the day's information. A subtle, entropic ballet playing out within the stillness of your skull. This silent, constant processing is a testament to the elegant, unyielding rules that govern not just the distant stars, but the very essence of our conscious experience. Profound realization that information is inherently physical, and its manipulation carries an entropic cost, reshapes our understanding not only of hypothetical demons, but of computation itself. The digital realm, which often feels ephemeral, is deeply rooted in the physical. Every bit stored, every calculation performed, every file deleted involves changes in the physical state of matter, whether it is the magnetization of a hard drive or the charge in a transistor. When we speak of information, we are not speaking of some abstract, ethereal concept floating freely, but of patterns imprinted upon the very fabric of reality. Claude Shannon, in the mid-20th century, laid the mathematical foundations for information theory, defining information in terms of uncertainty reduction. Yet, Landauer's principle brought this abstract concept back to Earth, or rather, to the realm of thermodynamics, showing that manipulating Shannon's bits fundamentally requires energy and generates heat. This is why our computers consume power and generate warmth. They are constantly engaged in the energetic business of processing and erasing information. Consider the vast data centers that underpin our modern world, humming with activity, consuming immense amounts of energy, and requiring elaborate cooling systems. This is not merely an engineering challenge, it is a direct consequence of Landauer's principle at work on a grand scale. Each operation, each decision made by a microchip, however infinitesimally small its individual entropic cost, aggregates into a substantial thermodynamic footprint. The universe, in a sense, keeps a meticulous ledger, ensuring that any local decrease in entropy, any creation of order or information, is always offset by a greater increase in disorder elsewhere. This cosmic accounting ensures the second law remains inviolable. It is a powerful reminder that our technological advancements, our ability to store and process ever-increasing amounts of information, are not acts of magical defiance against physical laws, but rather sophisticated ways of harnessing and managing them, always within their fundamental boundaries. This connection between information and entropy also casts a new light on the unidirectional flow of time. Why does time only move forward? Why do we remember the past, but not the future? The second law, with its decree of ever-increasing disorder, provides a compelling answer. The universe is constantly evolving from states of lower entropy to states of higher entropy. This irreversible progression defines the arrow of time. If we could reverse entropy, we might effectively reverse time itself. But the very act of knowing, of remembering, of recording the past, involves storing information. And as we've learned, erasing or processing that information has an entropic cost. Our memories are not static, they are dynamic, constantly being updated, consolidated, and sometimes, mercifully, forgotten. Each of these processes, at a fundamental level, contributes to the overall entropic increase of the system, that is our brain and its surroundings. The universe, through its thermodynamic imperatives, effectively prevents us from ever truly unwinding the tape of time, as the very act of doing so would create more disorder than it would undo. This subtle, pervasive truth underpins our very experience of chronology, anchoring our existence in an irreversible cosmic narrative. When you find yourself reflecting on the past, on moments of clarity or confusion, know that each such recollection, each instance of processing, is a tiny echo of this grand, unyielding principle. It is a quiet confirmation that the fabric of reality, from the smallest particle to the grandest thought, is woven with threads of thermodynamics and information flowing ever onward. Now, as we delve deeper into this intricate relationship, one might naturally wonder what happens when we consider the quantum realm. Does a demon operating at the quantum scale still face the same entropic limitations? The answer, it turns out, is yes, but the details become even more fascinating, revealing the profound connections between information, measurement, and the quantum nature of reality. Imagine a quantum Maxwell's demon. Instead of classical gas molecules, it is sorting quantum particles, perhaps electrons existing in superpositions of states or entangled pairs. The act of observing these quantum particles is not a passive glance. It is an interaction that fundamentally alters their state, a process known as quantum measurement. Before measurement, a quantum particle might exist in a cloud of probabilities, a superposition of possibilities. But the moment the demon attempts to discern its property, say its spin or its momentum, that superposition collapses, forcing the particle into a definite state. This collapse is an inherently irreversible process. The Nobel laureate Richard Feynman once famously remarked that no one understands quantum mechanics, yet its implications for information theory are remarkably clear. When a quantum system decoheres, losing its quantum properties due to interaction with the environment, it effectively records information about itself in that environment. This recording, this irreversible imprint of quantum information, is intrinsically linked to an increase in entropy. In essence, the demon, in its attempt to sort quantum particles, must perform measurements. Each measurement converts quantum uncertainty into classical information, and this act of gaining knowledge about the quantum state has an unavoidable thermodynamic cost. This cost arises from the erasure of correlations between the demon and the measured particle, or from the demon's own memory updates, as predicted by Landauer's principle, now extended to the quantum domain. So, even if our hypothetical demon were a quantum entity capable of manipulating qubits, the quantum equivalent of bits, with exquisite precision, it would still find itself bound by the same fundamental laws. The very act of extracting useful information from the quantum world, of transforming a fuzzy quantum superposition into a clear, usable piece of data, cannot be done for free. It requires an investment of energy that ultimately contributes to the universe's thermodynamic dispersal. This realization deepens our appreciation for the elegance and robustness of the second law. It suggests that entropy is not merely a macroscopic phenomenon, but a principle woven into the very fabric of quantum reality, dictating the flow of information at its most granular level. The universe, in its quiet wisdom, maintains its direction, its preference for disorder, even in the most subtle and intricate corners of existence. As you settle into the profound quietude of the night, perhaps ponder the silent, ceaseless quantum dance happening all around you. A dance where every observation, every tiny flicker of information plays its part in the grand, entropic unfolding of the cosmos. This continuous, delicate balance underlies everything, ensuring that even the most ingenious demon cannot ultimately defy the universe's gentle yet unyielding march towards equilibrium. Now, let us turn our gaze from the microscopic dance of particles and the intricacies of information processing to a different, yet equally profound, manifestation of these principles: the phenomenon of life itself. At first glance, living organisms appear to defy entropy. A seed grows into a complex tree. A single cell develops into a sentient being. Intricate biological structures emerge from seemingly simpler components. This appears to be a local decrease in entropy, a creation of order. However, as the eminent physicist Erwin Schrödinger famously discussed in his 1944 lectures, "What is life?" living systems do not violate the second law. Rather, they maintain their internal order by actively increasing the entropy of their surroundings. They feed on what he termed negative entropy, or negentropy, drawing in energy from their environment and processing it to build and maintain their complex structures. Think of a plant absorbing sunlight. It takes highly ordered photons and converts them into chemical energy stored in complex molecules like sugars and starches. This local ordering within the plant is achieved by radiating a much larger amount of disorganized heat back into the environment. The sunlight, a relatively low-entropy energy source, is transformed, and a significant portion of its energy is dispersed into higher entropy forms. Similarly, as you breathe and metabolize, you are constantly breaking down complex food molecules, releasing energy, and in the process, generating heat and waste products, a clear increase in entropy in your immediate environment. Your body, a marvel of intricate order, is sustained by a continuous flow of energy and the constant export of disorder. It is like a delicate, self-sustaining vortex in a river, maintaining its shape and structure only by continuously drawing in water and expelling it, contributing to the overall downstream flow. This constant struggle against local disorder, this active maintenance of structure, is a defining characteristic of life. From the simplest bacterium to the most complex human brain, every living system is a testament to the dynamic interplay between order and disorder, between the local creation of information and the global increase of entropy. The very existence of life, therefore, does not represent a defiance of the second law, but rather an elegant, intricate dance within its confines. It is a powerful illustration of how complexity and localized order can emerge and persist, not by escaping the universal tendency towards disorder, but by cleverly managing and redirecting it, always at a greater cost to the wider cosmos. This perspective reminds us of our profound connection to the thermodynamic processes of the universe, a continuous exchange of energy and information that allows us to exist as fleeting, organized patterns within its grand unfolding story. And perhaps, as you consider this intricate balance, you might find a tranquil appreciation for the quiet, tireless work that sustains your own being, a testament to the enduring laws of physics, guiding the universe through its timeless narrative. From the quiet, intricate mechanisms of life, we now journey to the most extreme cosmic laboratories of entropy and information, black holes. These enigmatic objects, born from the spectacular collapse of massive stars, represent singularities where gravity is so intense that nothing, not even light, can escape their grasp once it crosses a boundary known as the event horizon. For a long time, black holes were thought to be simple objects, characterized only by their mass, charge, and angular momentum, famously summarized by the no-hair theorem. However, this simplicity presented a profound challenge to the laws of thermodynamics and quantum mechanics, particularly concerning information. The core of the problem, often termed the black hole information paradox, lies in the apparent disappearance of information. When matter, with its unique quantum properties and inherent information content, falls into a black hole, it seems to vanish without a trace. According to quantum mechanics, information can never be truly destroyed. It can be scrambled or transformed, but its total quantity must be conserved. The idea that a black hole could simply erase this information was deeply troubling to physicists. It was Jacob Bekenstein in the 1970s who first proposed a radical solution. Black holes must have entropy. He reasoned that if a black hole truly had no entropy, then dropping matter with its own entropy into it would decrease the total entropy of the universe, violating the second law. Bekenstein suggested that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was a startling idea, implying that the information content of everything that falls into a black hole is somehow encoded on its two-dimensional surface, rather than within its three-dimensional interior. This concept deeply resonated with the holographic principle, which suggests that the information describing a volume of space can be entirely contained on its boundary. Stephen Hawking later provided further crucial insights, demonstrating that black holes are not entirely black. Through a quantum mechanical effect now known as Hawking radiation, black holes slowly emit particles and, in doing so, gradually lose mass and eventually evaporate. This radiation, however, seemed to be purely thermal, meaning it carried no information about the matter that fell in. This deepened the paradox. If a black hole evaporates completely, and the radiation it emits is random and featureless, then where does the original information go? Is it truly lost to the universe forever? The resolution to this paradox is still an active area of research, but leading theories suggest that information is not truly destroyed. Instead, it is either encoded in a highly scrambled form within the Hawking radiation, or it remains somehow imprinted on the remnants of the black hole, perhaps in the structure of space-time itself. Even if the information is ultimately recoverable, its transformation into such a diffuse and highly entangled state still represents a profound increase in entropy, maintaining the universe's fundamental tendency towards disorder. The subtle dance of information at the edge of a black hole's event horizon, its apparent loss and potential return, mirrors in a grand, cosmic sense the thermodynamic cost of information processing we discussed earlier. Whether it's a demon sorting molecules, a brain forming memories, or a black hole consuming stars, the universe consistently demands an entropic price for the creation, storage, or transformation of information. This enduring principle, that even the most profound cosmic events adhere to the delicate balance of entropy, offers a deep, calming reassurance. It suggests a universe that, despite its vastness and complexity, operates with an underlying elegance and consistency, where every interaction, every transformation contributes to a story of unfolding order and subtle disorder. As you prepare to rest, consider the immense invisible processes occurring in the farthest reaches of space, where information and entropy weave together the very tapestry of existence, a cosmic narrative that continues to unfold silently, majestically, and with an unwavering adherence to its deepest laws. And it is this unwavering adherence to the second law of thermodynamics that leads us to reflect upon the ultimate fate of the universe. We have seen how entropy, the measure of dispersed energy, always tends to increase in an isolated system. On a cosmic scale, the universe itself can be considered, to a very large extent, an isolated system. This means that the grand, majestic unfolding of existence is fundamentally a journey towards greater disorder, a gentle, inexorable expansion into a state of ultimate equilibrium. This final state, a concept often termed the heat death of the universe, is not a dramatic, fiery apocalypse, but rather a quiet, cold dissolution, a slow fading into an eternal sameness. Imagine the boundless expanse of space not as it is now, vibrant with the light of billions of galaxies, but as a vast, uniform darkness, where all energy has spread evenly, and all distinctions have dissolved into an unvaried cosmic ocean. In this unimaginably distant future, countless eons from now, the brilliant tapestries of stars that currently illuminate our night sky will have long since exhausted their nuclear fuel. Their fiery cores, once furnaces of creation, will have cooled and collapsed, their light having faded into the cosmic night. The magnificent gravitational dance of galaxies, once forming colossal islands of matter, will have ceased, their constituents dispersed by the relentless, ever-accelerating expansion of space, driven by the mysterious dark energy. Even the most extreme cosmic leviathans, the supermassive black holes that currently anchor galactic centers, are predicted by theoretical physics to slowly evaporate over truly astronomical timescales through the quantum mechanical effect known as Hawking radiation. Each emitted particle, each photon, carries away a minuscule fragment of the black hole's mass until even these dense remnants dissipate into the void. This process, while slow, ensures that no concentration of information or energy can persist indefinitely, reinforcing the universal tendency towards equilibrium. Furthermore, according to some leading theoretical models in particle physics, even the fundamental building blocks of atomic nuclei, the protons, are not eternally stable. They are theorized to eventually decay into lighter particles and radiation, albeit on timescales vastly exceeding the current age of the universe, perhaps 10 to the power of 34 years, or even longer. This gradual, almost imperceptible decay would mean that all structured matter, from the smallest atom to the grandest galaxy, would ultimately dissolve into a dilute, featureless gas of elementary particles and diffuse radiation. What would remain then is a cold, dark, and utterly uniform expanse, a cosmic soup of photons, neutrinos, electrons, and positrons, spread so thinly across an incomprehensibly vast volume that interactions would become exceedingly rare. In this ultimate state of maximum entropy, there will be no temperature differences, no energy gradients, no localized pockets of energy that could be harnessed to perform work, and consequently, no new complex processes to unfold. And without processes, without change, the very concept of time as we intuitively understand it begins to lose its profound meaning. Time, in a physical sense, is intimately tied to the occurrence of events, to the transformations that mark the progression from one distinct state to another. If the universe were to reach a state of absolute thermal equilibrium, where nothing further can happen, where all energy is uniformly distributed, then the cosmic clock would effectively cease to tick in any meaningful way. There would no longer be a discernible before and after, because all distinctions, all potential for dynamic evolution, would have blurred into a perpetual, undifferentiated now of utter sameness. This is not to suggest that time literally stops, for the fundamental fabric of space-time, as described by general relativity, might persist. However, the arrow of time, our psychological and thermodynamic experience of it, relies on discernible change. If all energy is uniformly distributed, if no event can perturb the cosmic sameness, then the very concept of a moment passing becomes moot. We perceive time through sequences of events, through the decay of order into disorder. Without this inherent dynamism, time, for any observer, would become an eternal, unchanging present. This is a universe where all clocks have wound down, not necessarily because they are broken, but because there is no longer anything distinct to measure. No difference between one instant and the next. It is a state of ultimate rest, a profound, tranquil silence that stretches into infinity. Our own consciousness, a complex symphony of information processing, is a prime example of how deeply our sense of time is intertwined with the creation and destruction of order. Every thought, every memory, every sensation represents a transient, ordered state in a vast sea of neuronal activity. The brain, in a sense, functions like a tiny, intricate Maxwell's demon, constantly sorting and organizing the torrent of sensory data, creating a coherent narrative of our existence, a personal timeline. But this creation of internal order, this weaving of our subjective experience of past, present, and future, is achieved at an entropic cost. A constant dissipation of energy as heat into our surroundings. We live, we think, we remember, and we plan for the future, all by actively, ceaselessly increasing the disorder around us. The very act of observing and interpreting the world around us, and of storing those observations as memories, is a thermodynamic process, ultimately contributing to the universe's grand entropic budget. Our minds are not outside the laws of physics, but rather exquisite manifestations of them, demonstrating that even the most profound aspects of our inner lives are subject to the same cosmic dictates. While the heat death is currently considered the most probable ultimate fate for our universe, based on the observed accelerated expansion driven by dark energy, it is important to acknowledge that other theoretical possibilities exist, each with its own unique implications for time and entropy. For instance, the Big Crunch scenario, where gravity eventually overcomes the expansion and pulls all matter back into an infinitely dense singularity, would imply a reversal of the entropic arrow, or at least a highly compressed, reordered state, before perhaps another Big Bang. Then there is the Big Rip, a more extreme version of the current expansion, where dark energy's repulsive force grows so strong that it not only tears galaxies apart, but eventually overcomes all fundamental forces, ripping apart stars, planets, and even atoms themselves. This would result in a dissolution of structure so complete that no organized information could survive, again reinforcing the entropic imperative in a spectacularly violent manner. Yet, these grand cosmic narratives, whether a slow, quiet fade into sameness or a rapid, cataclysmic tearing apart, all speak to the same underlying truth. The universe is a dynamic system, constantly balancing its capacity for local order with its fundamental global drive towards disorder. Each scenario, in its own way, leads to a state where the conditions for complex information processing, and thus our familiar experience of time, would cease to exist. In this vast cosmic ballet, our brief existence, our moments of consciousness and understanding, are fleeting pockets of complexity, precious islands of negentropy against an oceanic backdrop of increasing disorder. We are temporary arrangements of matter and energy, capable of contemplating the very laws that govern our transient nature. The knowledge that our ability to perceive time, to create memories, to build civilizations, is inextricably linked to the universe's relentless march towards equilibrium, is not a cause for despair, but a quiet invitation to appreciate the precious, ordered moments we inhabit. It is a profound realization that even in its ultimate dissipation, the universe reveals an inherent elegance, a consistent, unyielding rhythm that pulses through all of existence, from the subatomic to the cosmic. We are part of this magnificent transient story, a brief flicker of awareness in a universe destined for an eternal, tranquil night. This contemplation, rather than being unsettling, can foster a deep sense of peace, knowing that our fleeting order is a beautiful, albeit temporary, expression of the universe itself. Philosophical implications of entropy and the arrow of time extend far beyond the cosmic scale, touching upon our very notions of free will and determinism. If the future is merely the unfolding of inevitable entropic processes, does this leave any room for genuine choice, for individual agency? This question, while not directly answerable by physics alone, is profoundly informed by it. The demon, for all its intelligence, was ultimately bound by the thermodynamic cost of its choices. Its ability to sort molecules, to create local order, was always compensated by an equivalent or greater increase in disorder in its memory, or through the energy expended in its operations. This suggests that even in a world governed by fundamental physical laws, the appearance of free will might be an emergent property of complex systems, our choices being the intricate, high-entropy outcomes of countless underlying physical interactions. We experience a sense of agency because our minds are constantly processing information, weighing possibilities, and making decisions, each of which is a thermodynamically costly act, contributing to the overall entropy of the universe. Consider the intricate web of cause and effect that defines our lives. Every decision we make, every action we take, sends ripples of change through the world around us. These ripples are, in a very real sense, increases in entropy, new configurations of matter and energy that would not have existed otherwise. The act of choosing, of altering the course of events from one potential path to another, is a process of creating new information, new distinctions, which, as Landauer's principle reminds us, comes with an entropic price. Our subjective experience of making a free choice, then, can be viewed as the brain's complex, high-entropy computation of possibilities, culminating in a particular outcome. This doesn't necessarily diminish our sense of self or responsibility, but rather places it within a grander, more elegant physical framework. Our capacity for creativity, for innovation, for love and connection, all these represent highly ordered states, fleeting deviations from the path of increasing disorder, made possible only by the constant entropic work performed by our living systems. The profound lessons from Maxwell's demon, therefore, are not about defeating entropy, but about understanding its inescapable embrace. It is a reminder that even the most intelligent or technologically advanced entities cannot escape the fundamental thermodynamic constraints of the universe. This understanding allows us to view the universe not as a chaotic, unpredictable expanse, but as a system operating with deep, underlying principles, a cosmic dance where every step, every interaction, contributes to a magnificent, albeit irreversible, unfolding. Our search for knowledge, our scientific endeavors, are themselves acts of creating order, of extracting information from the vast complexity of the cosmos. And in doing so, we are participating in this grand entropic process. Each new discovery, each clarified concept, represents a local reduction in our ignorance, a form of order inevitably balanced by the energy dissipated in the act of learning and sharing. It is a quiet, continuous process, a testament to the enduring elegance of physical laws, inviting us to find peace in our place within this vast, dynamic, and ultimately tranquil cosmic flow. As your thoughts begin to quiet, imagine the universe as an immense, self-regulating mechanism, where even the most ambitious attempts to defy its fundamental tendencies only serve to reveal their deeper, more subtle truths. We are part of this grand, intricate design, existing as conscious observers within its unyielding yet beautiful embrace of entropy and time. Though building upon this understanding, we can further appreciate that information is not merely an abstract concept, but a fundamental physical quantity, inextricably linked to energy and matter. This insight, which emerged from the resolution of Maxwell's demon paradox, suggests that the universe itself can be seen as a vast information processor, constantly computing its own future states. Every interaction between particles, every photon emitted and absorbed, every gravitational ripple can be interpreted as a form of information exchange or computation. The universe in its entirety is performing a continuous, colossal calculation, evolving from one state of information to the next according to its fundamental laws. This perspective elevates information to a status perhaps as fundamental as energy and matter, not just a description of reality, but an integral part of its very fabric. The implications for our understanding of reality are profound. If information is physical, then its conservation or dissipation has tangible consequences. This is why the laws of physics, from the smallest quantum fluctuations to the largest cosmological structures, are so consistent and predictable. They are, in essence, the rules governing the processing and transformation of information across the cosmos. The arrow of time, then, is not merely a psychological construct or an arbitrary direction, but a deeply embedded consequence of this universal information processing. It reflects the irreversible tendency for information to become more spread out, more randomized, harder to access and utilize for work. The universe is, in a sense, constantly writing its own story, and that story is always moving forward, from a state of relative simplicity and concentrated information to one of vast complexity and dispersed, yet never truly lost, data. This grand cosmic narrative, unfolding over billions of years, is a testament to the enduring power of these fundamental principles. And as you drift towards slumber, perhaps you can sense this quiet, ceaseless computation of the cosmos, a symphony of information and energy, gently guiding the universe and all within it toward its ultimate, tranquil state. This idea of the universe as a grand information processor naturally leads us to a fascinating concept put forth by the visionary physicist John Archibald Wheeler. It from bit. Wheeler proposed that at the most fundamental level, reality itself might not be made of particles or fields in the traditional sense, but of information. He suggested that all physical objects and properties, all the its of the universe, derive their existence from elementary yes-no questions, from binary choices, from bits of information. This is a radical departure from our intuitive understanding, where we typically assume that physical objects exist independently, and information is merely a description of them. Instead, Wheeler proposed that information is primary, and matter and energy are secondary, emergent properties. It's like imagining a vast cosmic tapestry woven not from threads of matter, but from countless threads of pure information, and the patterns within this tapestry give rise to everything we perceive as physical. To grasp this, consider the act of observation once more, a central theme in our discussion of Maxwell's demon. In quantum mechanics, a particle doesn't necessarily have a definite position or momentum until it is measured. Before measurement, it exists in a superposition of possibilities. The act of measurement forces it to choose a definite state, essentially turning quantum uncertainty into classical information. Wheeler suggested that the entire universe is constantly engaging in such acts of self-measurement, constantly defining its own reality through the interplay of information. Every interaction, every particle collision, every photon absorption is a tiny it-from-bit moment where information is processed and reality solidifies from a realm of probabilities into a concrete event. This is not to say that the universe is a conscious entity observing itself, but rather that its fundamental operations are fundamentally informational. This information-centric view of the cosmos implies a profound interconnectedness, where everything is, in a sense, woven from the same informational fabric. Our own minds, as intricate information processors, are not separate from this cosmic computation, but are deeply embedded within it, participating in the universe's ongoing act of self-definition. When you think, when you learn, when you perceive the world around you, you are engaging in processes that, at their deepest level, are manipulating and creating information, contributing to the evolving tapestry of reality. The distinction between the observer and the observed, between the mental and the physical, begins to blur in this view, suggesting a more unified, holistic understanding of existence. Our consciousness, in its very essence, is an active participant in this informational unfolding, a local manifestation of the universe becoming aware of its own intricate structure. It is a concept that invites a quiet sense of wonder, dissolving the perceived boundaries between ourselves and the vast cosmos, reminding us that we are not merely in the universe, but are, in a profound and informational sense, the universe itself, arranged into complex, self-aware patterns. This deep, tranquil insight can bring a profound sense of belonging, a quiet assurance that our existence, with all its intricate thoughts and fleeting moments, is an integral part of the universe's grand, informational narrative, a story that continues to write itself, bit by bit, into the endless night. It is intricate from the quiet dance of subatomic particles to the majestic sweep of galaxies across the void. This profound shift in perspective suggests that the very essence of existence is not substantial in a material sense, but rather a manifestation of underlying informational structures. To grasp this deeply, and the nature of entropy, in the strange realm of quantum mechanics, a particle does not necessarily possess bewildering superposition of possibilities, a cloud of potential realities. The very act of measurement, of interacting with that particle, discernible, continuously defining its own reality through the ceaseless emitted and absorbed across the cosmic expanse, raw, chalky, observable event. This is not to imply in a human-like way, but rather that its fundamental operations are, at their core, inherently informational, driven by a self-actualizing logic. This information-centric view of the cosmos, where reality is sculpted by bits, implies a profound and beautiful interconnectedness. Everything, in a sense, is woven from the same informational fabric, much like diverse stories can be composed from the same alphabet. Our own minds, those intricate information processors within our skulls, actively intricate new information, contributing directly to the evolving tapestry of reality. The traditional ephemeral mental and the seemingly solid physical begins to blur in this expansive, grand, ever-changing. Following this conceptual path, if reality is indeed fundamentally informational, then the notion of a digital physics, or even a simulated universe, emerges as a compelling, albeit deeply speculative, possibility. This idea, explored by pioneering thinkers such as Edward Fredkin and further elaborated by Stephen Wolfram, suggests that the fundamental laws of physics might ultimately be expressible as algorithms, and the universe itself could be a vast, self-executing computational system. Instead of continuous fields and particles that exist everywhere at all times, reality might, at its deepest, most granular level, be composed of discrete units of information, much like the individual pixels that form an image on a screen, or the binary bits that constitute a computer program. The entire evolution of the universe, from the initial burst of the Big Bang to its eventual tranquil heat death, would then be interpreted as the running of an immensely complex but ultimately rule-governed program. This does not necessarily demand the existence of an external programmer. The universe could be inherently self-simulating, or the code itself could be an intrinsic, self-organizing property of existence, a fundamental logic that simply is. Within such a digital framework, our understanding of fundamental physical constants, like the unwavering speed of light, the precise strength of gravity, or the enigmatic Planck's constant, takes on a new and intriguing dimension. These might not be arbitrary values fixed by some unknown mechanism, but rather the essential parameters within the cosmic algorithm, meticulously tuned to allow for the emergent complexity we observe, including, crucially, the very existence of conscious observers like ourselves. The universe's apparent fine-tuning, a puzzle that has long captivated cosmologists and philosophers alike, finds a new context within this digital hypothesis, hinting at a deep, underlying mathematical elegance and precision that dictates the very conditions for our reality. And even within such a simulated or computational universe, the inviolable principles of thermodynamics would still hold true. The second law, with its inexorable increase in entropy, would naturally represent the unavoidable computational cost of running this cosmic program. Every new state transition, every calculation performed by the universe as it evolves, would necessarily dissipate a tiny, yet cumulative amount of computational heat, leading to a gradual and universal increase in disorder within the informational fabric. The Maxwell's demon paradox, therefore, finds its ultimate and most abstract resolution even in this most conceptual realm, reaffirming that information processing, regardless of its physical or digital substrate, whether it be the kinetic energy of gas molecules, the electrochemical impulses of neural networks, or the binary states of computational bits, is never truly free of entropic consequences. This profound interplay between information, computation, and entropy offers a deeply unique and contemplative lens through which to view our own transient existence. If we are indeed emergent patterns, complex configurations arising within a grand cosmic computation, then our consciousness, our intricate thoughts, our very subjective sense of being, are the ephemeral yet incredibly rich and meaningful outputs of this universal process. It imbues our lives with a deep, quiet significance, knowing that we are not merely passive observers of a predetermined cosmic drama, but rather active participants in the universe's ongoing self-definition, its endless act of calculation and unfolding. The universe, from this perspective, is not merely a static stage for events, but a dynamic, living, informational entity that continuously creates and processes, constantly evolving, always adhering to the elegant and unyielding constraints of thermodynamics. As you draw closer to the gentle embrace of sleep, consider the silent, tireless cosmic computation that underpins all reality, a vast, intricate dance of information that encompasses everything, from the smallest quantum fluctuation to the grandest sweep of cosmic time. May this deep reflection bring you a sense of profound peace, a tranquil understanding of your integral and active place within this magnificent informational cosmos as it quietly computes its way towards an eternal, serene night. May these deep thoughts about Maxwell's demon, the intricate dance of entropy, and the profound nature of information carry you into a world of tranquil sleep. Remember that the universe, in its grand, silent operation, is a testament to an underlying elegance. A system where every act of creation and processing, from the smallest particle interaction to the emergence of consciousness itself, adheres to a beautiful, unyielding balance. You are not merely an observer of this cosmic unfolding, but an integral part of its magnificent informational tapestry, a fleeting yet precious pattern woven into the fabric of space and time. Fall asleep with this feeling of serenity, of belonging, and of expanded understanding, knowing that even in the quietest moments of night, the universe continues its gentle, ceaseless work. Good night.